of laser diagnostics and spectroscopy 2.1. And let's start our session at last with a 15-minute delay, but never mind. Today we have, in this session, we have 4 talks. And the first one is entitled Biodegradable Luminescent Porous Silicon Nanoparticles in Cancer Diagnosis and Therapy, and it will be delivered by Dr. Sminkina. Would you like to take the floor?
Hello, dear colleagues. Good morning. My name is Lyubov Sminkina, and let me introduce my report. But first, I want to say big thanks for organizing committee to give me opportunities to make a report on this such a nice conference with such nice auditory. So thank you very much. Так. Let's start the briefly introduction and what about outline of my talk. So first introduction, and then I show you the photoluminescent properties of porous silicon and method for production of porous silicon and porous silicon nanoparticles, and then we discussed about biocompatibility and biodegradability properties of porous silicon nanoparticles for the application in biomedicine, and then briefly about Raman scattering and luminescent microscopy techniques and to monitoring the presence of porous silicon nanoparticles inside the cells and the drug release inside the cells from these nanoparticles, and then about sonosensitizing, photosensitizing, and radiofrequency sensitizing properties of porous silicon, which we can use in custom therapy. So let's start with silicon. So why we choose silicon to make silicon nanoparticles and to use it in biomedicine. So the silicon is the second most abundant chemical element in Earth's crust. So we have no problem where we can find silicon, and silicon is the basis of the modern semiconductor electronics. So we have no problem to produce the silicon wafers and then produce nanoparticles from these silicon wafers. And what is the most interesting for future biomedical application of silicon, that the silicon is the was just curious when in Bell Lab Dr. Uller with his 5 polished silicon films for microelectronic, so they suddenly expect that on the top of silicon they, after electrochemical aging, produced some strange interfering film. And but unfortunately, at that time, the method of electron microscopy was not developed very well, and only after several years, scientists start to investigate this film and expect that this is porous silicon film. So it's very interesting story. But a lot of work with porous silicon and porous silicon films started after the discovering of Lee Cannon in 1990. So he discovered the photoluminescent properties of porous silicon at room temperature photoluminescent properties, and proposed a quantum confinement model to describe the photoluminescent properties. And then in 1995, also Professor Lee Cannon discovered the biocompatibility properties of porous silicon and propose its use in biomedicine. And till this time, we have a lot of studies every year, thousands of works about porous silicon and its photoluminescent properties and its biomedical properties. So it's a very interesting material. What about photoluminescent? Porous silicon, this is a sponge-like structure, composite structure, which consists of small silicon nanocrystals, so it's also can named as silicon quantum dots, and pores. And what is interesting for optoelectronic application and as well for biomedical application as luminescent labels, then we can tune the maximum of photoluminescent by tuning the size of these nanocrystals. So the size of these nanocrystals, so the maximum of peak position, it's depend from the size of silicon nanocrystals. So when we when the size became smaller, the maximum shift to blue spectrum region. So it's very, very interesting for its application. And what about nanosilicon and what we can do in my lab? So we propose different methods for reproducible synthesis, different porous silicon nanostructure and porous silicon nanoparticles with tunable properties. And we can, the possibility to surface functionalization of such nanoparticles and to use it in drug delivery, in diagnostics, with different optic techniques, and as well as we study biocompatibility, biodegradability, and possibility of activation of different therapeutic properties by external physical influence. So. Now I briefly describe you how we produce our porous silicon films. First, we of course use the same electrochemical etching, and we use here different type of silicon wafers with different doping level. When we use 10-20 ohm per centimeter doping level, so we can produce microporous silicon films, which consist of 2 nanometer sizes silicon quantum dots, and also 2 nanometer sizes silicon pores in these porous silicon films. And such films, as well as porous suspension of porous silicon nanoparticles, have very, very nice and brightly photoluminescent properties in red spectrum region, which is very nice for future bioapplication of such nanoparticles. And also we can simply produce our nanoparticles by mechanically milling of our films in ball machine or by ultrasound. So it's very easy way to produce photoluminescent silicon and porous silicon nanoparticles. Also, we can use another type, highly doped crystalline silicon substrate, and we can produce mesoporous as well as macroporous porous silicon films. So we can produce the nanoparticles with mesoporous structure. So the pore size in such nanoparticles is near 10-50 nanometers. This is very nice size for future drug loading and drug release of from these nanoparticles. So for using such nanoparticles as nanocontainers. Also. We develop a method of perforated etching. So now we can use different current density and produce mesoporous film and macroporous film. And when we crash this perforated etched film by ball machine or by ultrasound fragmentation, it's mostly crashed in these sizes where is macroporous films present, and so we can produce nanoparticles with predicted sizes, with monodispersity size distribution. So it's also very nice for its future bioapplication. Also, we can use another method, metal-assisted chemical etching of crystalline silicon with different double level as well to produce non-porous and porous silicon nanowires. And then by ultrasound fragmentation, we can produce non-porous or porous silicon nanoparticles. And also such silicon nanoparticles demonstrate very nice and effective photoluminescent properties in red spectrum region, and we then can use it as luminescent labels as well. So what about the morphology, structural, physicochemical properties of the porous silicon nanoparticles which we obtained? So porous silica, the typical transmission electron microscope image you can see on the left. So such porous silicon nanoparticles is the nanoflakes of porous silicon films, and such nanoparticles consist of porous structure. So it's also the composite structure. So it consists of small nanocrystals and pores. And also we can use the size of nanocrystals, we can use the size of pores, but of course for bioapplication we can achieve photoluminescent nanocrystals and pores with diameter near 15 nanometers, so we can do it. Mean diameter of our nanoparticles is about 100 nanometers, so it's very nice for bioapplication too. And here you can see the absorption spectra. So such suspension is transparent in visible and infrared, red and infrared spectrum regions, so also very nice for bioapplication. And so this porous structure we can use for drug loading, so I described it before. And what about biocompatibility? Of course, we have different studies with different colleagues from all the world and investigate biocompatibility properties of our nanoparticles with absolutely different types of cells, as well as cancer, different types of cancer cells, and also fibroblast cells, and also with cardiomyocyte, because it's very important to investigate how nanoparticles influence on our heart when we use it in treatment of different disease. And with all of these types of cells, we cannot find the toxicity properties up to a concentration of half milligram per milliliter, so it's very nice. And what is also important, that our nanoparticles didn't demonstrate toxicity properties during the prolonged time incubation up to 10 days, so it's also very nice for its future bioapplication. And also we did several in vivo experiments and also demonstrated that our nanoparticles non-toxic up to concentration of 50 milligrams per kilogram after intravenous administration. And also they didn't demonstrate any teratogenic and genotoxic effect on mice when they were intraperinatal administrated. So it's also very interesting. What about how we can use photoluminescent properties? So in this slide you can see the different pictures of cancer cells which were incubated with luminescent porous silicon nanoparticles, different type. So produced for microporous silicon films, from porous silicon nanowires, or perforated agent porous silicon films. So all of these nanoparticles can use as luminescent labels. And also you can see that such nanoparticles can penetrate inside the cells and locate predominantly in cell cytoplasm. So we can use our nanoparticles as luminescent labels. And also we can use high resolution structural illumination microscopy. The study we were made with our German colleagues from Institute of Photonic Technology, Jena. And in this study we use very, very weak concentration of silicon nanoparticles, of luminescent silicon nanoparticles, and try to study how it penetrates inside the cell. So we observed that after 5-hour incubation, they located on the cell membrane, and then after 24-hour incubation, the nanoparticles locate in cell cytoplasm. So you can see these breadpoints inside the cell cytoplasm on this video image. So what about Raman scattering of porous silicon? So I really like this technique to investigate the properties of porous silicon and how porous silicon nanoparticles interact with cells. So I think that this technique is very informative, this is not destructive, and we can get a lot of interesting results. We all know, of course, that crystalline silicon have their own sharp peak, Raman peak, and near 50-20 centimeter -1. So as well as silicon nanocrystals, as well as porous silicon, but Raman peak from porous silicon is broadening because of different size distribution and because of quantum confinement in such nanocrystals. And also peak position is dependent from the diameter of silicon nanocrystals. So we can measure the diameter of silicon nanocrystals by measuring the Raman spectra of our nanocrystals. And also when silicon nanoparticles start to oxidize, start to dissolve as well, we can also observe the broad peak from amorphous silicon. So it's very nice for future application of Raman scattering methods to investigate how our silicon nanoparticles interact with cells. On this slide you can see the spectra which we obtain from cells which we incubate 24 hours with our porous silicon nanoparticles, and then we made vertex component analysis of such spectra. So we measure mapping, and then when we find signal from cell component, we put on map blue point, and when we find the signal from crystalline silicon, we can put red point, and so we can reconstruct mapping of our cells, view of our cells, and we can find where inside the cells nanoparticles is located. So on this slide you can see X, Y, and XZ images, and so you can see that nanoparticles locate inside the cell cytoplasm, so we can observe the crystalline silicon peak inside the cell cytoplasm, and then we investigate how with Raman scattering how nanoparticles interact with cells. So we can find that after 6-9 hours nanoparticles locate on cell membrane and then start to penetrate inside the cell cytoplasm, and then we decided to investigate for very, very long times, for 2 weeks, near 2 weeks, how nanoparticles interact with cells, and we discovered that after 48 hours of incubation, we also have the signal from the amorphous silicon. So we can see amorphization of our silicon nanoparticles when they incubate inside the cells for a prolonged time period. And after near 2 weeks, we can see the very, very weak signal from crystalline silicon and very, very broad in spectra. And it's because the dissolution of our nanoparticles when they incubated with cells for a prolonged time period. Also, we can use our nanoparticles as nanocontainers, and we load different type of drugs inside the nanoparticles, and then we can use also Raman scattering to investigate how nanoparticles, nanocontainers interact with cells, because the drugs also have their own Raman peak position in Raman spectra. So we can investigate with Raman scattering how nanoparticles locate inside the cells and how they release the drug. So it's very interesting. Also, because of nanoparticles we have not find toxicity properties, we can use our nanoparticles to initiate the apoptosis or necrosis process inside the cell. So it's also very important. And then so free slides. And also we can use, because of photoluminescent properties of our nanoparticles, we can use this as photosensitizers of singlet oxygen. And singlet oxygen have extremely oxidizing properties, and we can use then such properties for destroying the cancer cells, for photodynamic therapy. And also we showed that our nanoparticles demonstrate activation of therapeutic ultrasound because of cavitation threshold is such suspension. So we need a very, very low intensity ultrasound to enhance cavitation in our suspension, and we can use this effect to destroy the cells to cancer treatment. And also we discovered that our nanoparticles can play a role as a sensitizer for therapeutic radiofrequency radiation. So under radiofrequency radiation, the temperature enhances very quickly with the presence of silicon nanoparticles, and we can use this effect also for cancer treatment. So briefly conclusion, so I think that porous silicon nanoparticles is a very, very promising material for biomedical application because of interesting physical properties which we can use for biomedicine, for labeling of cancer cells, for treatment of cancer cells. And I want to say acknowledgements for my colleagues from for our Moscow State University, from different universities around the world, and thank you for your kind attention.
Thank you for your extremely interesting talk. So, please, questions.
Thank you very much for your presentation. My question is it important the initial porosity of a film for your investigation, and is nanoparticles properties depends on it?
Yes, of course. So why porous? Why porous film? Because when we crash these films, the nanoparticles also have porous structure. So because of nanoparticles have a porous structure, it consists of small silicon nanocrystals and pores. And we can use pores for drug loading and then for drug release to cancer treatment. And we can use properties of silicon nanocrystals as photoluminescent properties for cancer labeling. And also such properties as sonosensitizing depends of porous structure, because solid nanoparticles enhance ultrasound not very much in compare with porous nanoparticles, and so also we can need the photoluminescence of our nanocrystals for photosensitizing as well as radiofrequency too. So, yeah.
Do you measure the porosity of your film?
Yes, of course. Of course. So.
And what methods?
Just one moment. So we can produce different porous silicon films, and of course we measure porosity. So from mesoporous film as well as for nanoparticles, we have pore size near 15 nanometers, and for microporous film we have the pore size near 2 nanometers. So we can tune the pore size when we produce of our porous silicon film and then porous silicon nanoparticles by the electrochemical etching method. So it's, yes, it's very important.
Please, more questions? And let me ask you, you've talked about drug release. How does it work?
So it's very important to have sustained drug release when you use nanoparticles. So if you have the standard method of cancer treatment, you just inject the drug and you have this concentration inside your blood. And when you use nanoparticles, the main idea is that nanoparticles can deliver the drug directly inside the cells, so without any toxicity properties on another healthy cells. And also they demonstrate sustained drug release, so drug release not delivered very quickly, so for prolonged time, and enhance more toxicity for cancer cells and localization of this drug toxicity. So this is very important for treatment of cancer. So you can use a very small amount of drug when you use nanoparticles in compare with the standard method of chemotherapy.
Okay, thank you. So let's thank the speaker again. And our next talk, laser spectroscopy of carbon nanoparticles in creation of multimodal nanosensors. And, so, Dr. Dolenko, would you please
Thank you.
start?
I want to thank the organizers of our conference for the opportunity of our results at this meeting. And okay. My talk is devoted to the research of dependence of carbon nanoparticles luminescence on the environmental particles, and to the creation on this base of multimodal nanosensors of these environmental parameters. Due to the active development of science and industry, where the remote and express monitoring content of different substances in multi-component media is hot topic. The creation of multimodal nanosensors remains relevant. And we know the nanosensors capable to measure only one or maximum two environmental parameter, but we want to elaborate scientific base to predict the efficiency of multimodal nanosensors capable to measure several parameters of environmental simultaneously. Why we consider carbon nanoparticles? Currently, these nanoparticles are most promising for nanosensory because carbon nanoparticles, namely carbon dots and nanodiamonds, have stable intense luminescence, sensitive to different environmental parameters. They are non-toxic, biocompatible, and they are such nanosensors can be used in technology waters, technology processes, ecology, and biomedicine. My talk will focus only on carbon dots because a good nanosensoric properties of nanodiamonds were discussed by Dr. Vlasov at the plenary session today. So I can say that the purpose of our research is the development of photoluminescence multimodal nanosensors based on carbon dots using laser spectroscopy and using machine learning, namely artificial neural networks. Laser spectroscopy provides the study of mechanism of parameters influence on CDPL and makes this method remote. And machine learning methods provides the multimodality of our nanosensors, that is, the ability of nanosensors to determine several parameters of environment simultaneously. And two tasks were set. Development of the photoluminescence carbon dots nanosensor for pH and temperature of liquid media, and development of photoluminescence carbon dots nanosensors for ions, including heavy metal cations in the environment. You can see the used experimental and mathematical method in our studies, and as the objects of our study were carbon dots of hydrothermal synthesis as environments, water, technological earth, media, technological real processes, media, protein, and liquid solution of the following salts were used. The carbon dots were synthesized by hydrothermal synthesis from citric acid and ethylene diamine in our laboratory, and you can see the following characteristic of this nanoparticle. It's important that their size in water were about 30 nanometer, and these nanoparticles have carboxyl, hydroxyl, and imine groups. Quantum will of PL of these nanoparticles was 58%. Task number 1. At the first stage, the dependence of CDPL intensity on the pH and temperature of liquid water was studied, and the concentration of nanoparticles is fixed, and it's equal 5 milligram, and the following you see the following range of pH and temperature change in our liquid solution. PL spectra was excited by laser radiation with wavelengths 405 nanometer, and under this excitation, CDPL spectra represent broad bands with maximum on the 520 nanometer. And to quantify the CDPL intensity, the parameter F0 was used. It's equal to the ratio of integral intensity of photoluminescence to integral intensity of valence Raman bands of OH groups of water. We obtained the dependencies of the parameter 0 on pH at different temperature and on temperature at different pH. The figure from on the left shows that when pH increases, the intensity decreases. And our results of experiments and our calculations using density functional theory published in these particles showed that this behavior of dependencies can be explained as follows. When pH decreases, the functional groups carboxyl, hydroxyl, and amide were deprotonated. The possibilities of aggregation of nanoparticles increases. As a result, CDPL intensity decreases. And the figure on the right showed that when temperature increases, CDPL intensity decreases. This may be explained by thermal activation of surface traps, or as well as thermally induced increase in the probability of non-radiative relaxation of excitation. But in all cases, we see that the CDPL intensity has a higher sensitivity to pH and temperature of liquid solution, and therefore carbon dots can be used as nanosensors of this parameter in liquid media. Our obtained dependencies are nonlinear and enough complex, and to solve these inverse two-parametric problems, the artificial neural network were used. To train the neural network, 5,600 PL spectra of CDX solution at different pH and different temperatures were obtained. And the entire, you can see the range of parameters changes. And the entire data set was divided randomly on training, validation, and test sets in the ratio 7 to 2 to 1. All PL intensity are considered as input features of network, and two value of pH and temperature are considered as output feature of network. To find the optimal artificial network, the perceptron with different number of hidden layers and different number of neurons in them were used. And as a result, the perceptron with two hidden layers and with such number of neurons provides the following accuracy of pH and temperature determination simultaneously. It is known that the quality of inverse problem solution depends on input data dimensionality, and the application of PL intensity over 10 neighboring channels of PL spectra allowed us to decrease the error of pH and temperature determination approximately twice. And to use carbon dots as nanosensors in biomedicine, the detection of upconversion luminescence of our carbon dots turned out to be essential. We know that under excitation of UCL, the autofluorescence of biological tissue is not excited, and excitation falls in the biological transparency window. We obtained the UCL of carbon dots with maximal intensity under excitation of radiation of parametric light generation with wavelengths 720. And we see that the dependence of UCL integral intensity on pH value has a linear section from pH it's equal to up 9. And the use of this linear section allowed us to measure pH of liquid media with such the following accuracy. The approbation of our carbon dots as nanosensors of pH and temperature values and carbon dots with luminescence in Stokes and anti-Stokes regions was carried out for chicken, egg, white, and parallel to spectra registration. The pH and temperature value in egg white were measured by pH electrode and thermocouple. And we see that the measurement of these parameters made by two independent methods are in good agreement. It should be noted that this agreement is already satisfactory results. Recall that the pH value in biological tissue vary from from 4 to H, and temperature during infection processes can vary up to 7 degrees. Let us consider task number 2. At the first stage, the dependence of the CDPL intensity on the type and concentration of ions of water were investigated for the following salts. And aqueous solution were prepared in such a way that concentration of carbon dots is fixed and concentration of salts varied in the following range. The CDPL luminescence of these solutions were excited both laser radiation and using spectrophlorimetry, which made it possible to obtain excitation emission matrix with dimensional D. And the obtained results showed that the following salts, all the following salts, have a little influence on the optical density spectra, except for iron ions, but they significantly affect on the PL intensity. And on the base of all spectral data analysis, the following row constructed, was constructed according to the degree of influence of ions on the PL intensity. And to elaborate the scientific base to predict the efficiency of our carbon dots, the types of PL intensity quotient were investigated using the Stern-Follmer theory. According to this theory, there are two types of PL quenching, static and dynamic. And if both mechanisms are implemented, we have the following quadratic function. The obtained dependencies of PL integral intensity on the concentration of metal cations does not the exact information about type of PL quenching. These dependencies is nonlinear and they deviate towards abscissa axis. And to determine the type of PL quenching, we obtained kinetic curves of CDPL decay in water for all the studies salts. You can the obtained kinetic curves were approximated by two exponential dependencies, and the obtained dependencies of lifetimes of CD luminophores on the concentration of metal cations allowed us to make estimations of their contributions of types of PL quenching. It was established that the inner filter effect is significant only for iron ions. The static quenching is significant for trivalent ions, and as two valent cations, they have a greater contribution of dynamic quenching, and lets us return to nanosensory. We have two conclusions. The CDPL intensity is most sensitive to the dynamic quenching, and the another criterion for selection of cations for nanosensors is the information about presence of ions in real technological waters. On this, with this consideration in mind, the following ions were chosen for our nanosensory, and the application of multi-layer perceptron and convolution neural networks allowed us to obtain the satisfactory accuracy of determination of concentration, the chosen ketones, and the augmentation of input data allowed us to reduce these errors, and the follows for each cation. And testing of our nanosensors is real factory technological waters indicate the large potential of our nanosensors for controlling of waste waters and technological water media, but the composition, ionic composition of these technological waters must be similar to the composition of our liquid studied solutions. it's here are my main conclusion, but they were discussed during my presentation. Thank you for your attention.
Thank you for your talk and questions.
Can you tell once again what is the origin of a sharp peak at the beginning of your presentation when you showed the PL spectra for quantum carbon dots?
I understand, yes. Sorry. Mm-hmm. The broad band is the photoluminescence, and the narrow peak it is Raman valence band of OH pitch, and this band cannot be visible if the concentration of carbon dots is large, and they are low concentration because we see this band.
Thank you very much for very interesting talk. But I have a very general question. Your group, together with your boss, Viktor Fadeev, started working with the neural networks, I think in 90s. I think it was one of the first group, yes. Not only in Russia, but in the world. And my question is now, what is the development of this technique? Is it all in your group? Is it only the power of computers, or it is something principle that you change in your networks that gives you really some, these results of multimode, for instance, sensor?
Thank you for your question. Currently, we became to use the new architecture of neural network, for instance, convolutional neural networks, and we use the methods of reduction of dimensionality or compressibility input data. And some months ago, we make a new step towards, because for the first time we used the augmentation of input data dimensionality, and this method allowed us to increase the number of input data, because when we studied biological tissue, the large number of set of spectra is very difficult to obtain.
Well.
Thank you very much for your talk. Actually, Sarah, you can find now a lot of works concerning the carbon nanowires. Could you compare what is better, carbon nanodots or carbon nanowires? Are they more sensitive, or what is the reason for?
In compare to, for example, nanodiamonds of fullerenes, the quantum yield of luminescence of carbon dots are much bigger. And for example, quantum yield of nanodiamonds is several, from 1 to 10 units, and our carbon dots have about 50% of luminescence. And I can compare with the information of our planar report. Dr. Vlasov talked about a nanodiamond as nanosensor of temperature. But it's important for these nanoparticles is the fixation of position of luminescence of CV defects And these nanoparticles are, this luminescence is insensitive to change of environmental parameters. And we study the intensity of photoluminescence.
Okay, dear colleagues, I'm sure there are still questions, but we have to follow the schedule, and let's thank the speaker again. And let's proceed. Our third talk should be delivered by Dr. Kharkov. Is he here? No. So then let's proceed to the fourth talk, ultra-fast spectroscopy of tungsten disulfide nanotubes. So, Dr. Paukov.
Mm-hmm. Yeah. Okay, yeah. So thank you. Today I'm going to, well, my name is Maxim. I'm a PhD student of the first year at MIPT in the Center for Photonics and 2D Materials. And today I'm going to deliver a talk on ultrafast spectroscopy of tungsten disulfide nanotubes. So we should understand what ultrafast spectroscopy is, what tungsten disulfide is, and what a nanotube is. So we will briefly discuss all of these things. So tungsten disulfide belongs to the class of the transitional metal dichalcogenides. Most of them are known as prominent semiconductors and a unique platform for the observation of various physical solid-state phenomena. And nanotubes are quasi-one-dimensional structures. In picture in this slide in A and B, you can see the transmission and scanning electron microscopy of the samples which we studied. These were the films of tungsten disulfide nanotubes in the form of film. They were randomly oriented, as it can be seen in the picture B. So these tubes tend to be multi-volt. In our case, it was about from 15 to 20 volts. They are quite big in diameter. The average diameter is estimated as 80 nanometers. And at the same time, they are not too long, about 1 micron. And well, it is known that carbon nanotubes, for instance, they are much longer. And we studied two types of samples, so pristine films and films doped with the hydrochloride of gold. The concentration was 15 millimoles. Yeah, and in this slide you can see the general optical characterization. So we performed Raman spectroscopy shown in D, measured the photoluminescence in C, and the absorption in the visible range. And there I marked the effect of the doping and also the position of the A, B, C, and D excitons. So the bound states of the hole and electron. Also, it is interesting to see that there is a sharp dip in the absorption spectra, which is mostly ascribed to exciton polariton modes, which can exist in such broad tubes. And of course, it is interesting to see in the photoluminescent spectra some sidebands which are mostly ascribed to the localized excitons, and the emergence of trions with the increasing the intensity of the laser radiation. So this is about tungsten disulfide nanotubes, and the general methods which we utilized in the current research were optical pump terahertz probe and transient absorption spectroscopy in the visible range. So you can see here the principal schemes of these setups. Generally, we divide the fundamental laser radiation into two paths and create, if we want, for instance, transient absorption spectroscopy, we generate supercontinuum for probing and one wavelength for pumping. In our case, it was 400 nanometers, so we covered the energies of A and B excitons, and in optical pump terahertz probe spectroscopy, so it is just some kind of the improvement of the terahertz time domain spectroscopy by adding the extra path which pumps the sample, and we can measure the photo excitation. So the transient absorption spectroscopy was performed in the Institute of Spectroscopy in Troitsk, and optical pump terahertz probe was performed in England in the University of Warwick in the group of the Professor James Lloyd Hughes. But now the same scheme exists in the Institute of General Physics, so the the method which we use for the description of the data is the thin film approximation. It means that that the sample, films of tungsten disulfide were attached to the Z-cut quartz substrate, which was much thicker than the sample, and we considered that we can neglect all Fabry-Perot resonances and take into account on the first term there. And it allowed us to estimate the photoconductivity in the terahertz measurements, which is proportional to the change of the detected terahertz signal with photoexcitation and without it. So these are methods which we use. Now we can see what was revealed. So first we are going to talk about transient absorption spectroscopy. It allowed us to check the excitons. So in the first line you can see the pictures, the maps of the change of optical density, which was created by photoexcitation. And the dashed lines mark the position of the excitons which we defined from the equilibrium optical absorption measurements. So you can see there are different effects. So there is a blue shift of the exciton positions, which can be explained by the band gap renormalization, the effect that was discovered recently in some papers. Yeah, of course, photo bleaching and photo-induced absorption lines, and so we decided to extract the background, and you can see the bottom line of the graphs, and it is interesting to see that well, it is hard to see, but when you look at these graphs for too long, you see that the A exciton splits into two bands, and it is a sign of the existing trions in this system. So trions are charged excitons, either positive or negative. In order to understand, to obtain some information from it, we have the experimental data, and also we decided to create a model with writing equations and to track the position of a exciton, I mean the time dependence of the amplitude of the A exciton. So you can see it in this column, in the last column. So there are just some modifications. The general data is in the picture C, and then some calculations. And it is interesting to understand the process of diffusion of the excitons in such a system. So we use this rate equation, which shows the dimensionality in this power dE is the dimensionality of the exciton diffusion. And in our quasi-one-dimensional system, the diffusion of the excitons exists in the dimensions of 2D, either 3D. And it is interesting, however, it is might be explained because the Bohr radius for our nanotubes is estimated to be about 2 nanometers, and the diameter of the nanotubes, which I showed, for instance, was about 80 nanometers, and also the length of the nanotube is quite big. And by the way, we have multi-volt structure. So this assumption is so might take place, I would say. So moving to the optical pump terahertz probe, we can measure with this setup two types of data. First is the frequency dependence of photoconductivity, and also we can track the data with the time, so we can measure transient. In this slide you can see the measurements of the extractant photoconductance, and depending on various fluencies and times, and we mark there the position of the zero crossing of the imaginary part in order to see the changes, and we phenomenologically fitted this data within a localized surface plasmon model, and the formula is given at the top of the slide, where the resonant frequency is this zero crossing is given also here, and so the results are quite understandable. If the more we pump, the more photo-induced charges we have, so it means that this frequency can move. And if we wait for some relaxation, again, it also moves this frequency. And also we can gain the scattering rate from these results, and it can help us to estimate the mobility of our samples, and it is interesting that is about 300 centimeters squared volts in the power of -1 seconds reverse seconds. So in the experiments with the transistors which are made on the single tungsten disulfide nanotubes, the result is a bit smaller, and as a result, so we can use this setup to understand, for instance, the mobility of the photo-induced charges, and this method is non-contact and it requires no special geometry, so it's quite important sometimes. And so the dynamics, the transient probed by optical pump terahertz probe is shown there. We fitted the results within bi-exponential model. So in order to understand what these exponents mean, we first estimated the length of the diffusion, knowing the scattering rate from the frequency measurements. And it was about 12 nanometers. and the nanotubes itself are much longer. So these dynamics cannot be explained in terms of the scattering on boundaries. And also it is seen that there is no strict connection with fluence. If you can see at the slope at the 0 time difference, and these times of this exponential decays for pristine and doped samples are shown there. So it is interesting that there is a saturation of tau 1 and something like the same behavior with tau 2, but on a much larger time scale. Yeah, so one fast component and one not that fast component, but still. Yeah, and now we arrive at conclusions. So the methods of transient absorption spectroscopy and optical pump terahertz probe allowed us to probe the dynamics in different scales of wavelength. We propose the contribution of free charge carriers, excitons, the presence of defects. So the processes of diffusion were studied of excitons, and also we measured the photoconductivity in the terahertz range, and it revealed the plasmonic response and the defect-mediated dynamics. More results of this research may be found in the paper, which is now under review, but we hope that soon we will get in touch with our reviewers and everything will be okay. Also, as a conclusion, I wanted to say that the interest of this work is first in the fact that tungsten disulfide nanotubes are known for so long, but nobody actually have studied them under these ultrafast spectroscopies almost. Mostly 2D materials and their 2D counterparts. Secondly, the general idea of combining several types of spectroscopies and these particular types of spectroscopy when we can vary the pump and probe is a very interesting and interesting tool to study various phenomena in solid-state physics. Thank you for your attention. If you have any questions, I'd be happy to answer them, and you can find some contacts, and if you wish, you can contact me via this email. Thank you.
Thank you very much for your interesting presentation. I have actually I have first just remark. You said that nobody studied dynamics of transition metal decoupling.
Somebody have, yeah.
Yes, we studied it for last 5 years. Okay, but I have a question also, and have publications in Q1 and other. So my question is, I think I missed how you distinguish charge carrier dynamics and exciton dynamics in your experiments.
Well, mostly we ascribe the dynamics in the visible range to excitons and in terahertz range to free charge response.
Okay, so I have one question. Thank you for so interesting talk. So, please, could you display a second slide?
The second one, yeah?
Yeah. Okay. So you interpret some absorption peak by, I see, direct transitions, and this is a panel below in the right angle. So what you can you say something about Urbach energy for this system? I suppose you have considered only A, B, C, D transitions. Some of them interband and some I say intraband. Yes? Okay, so but in my opinion this system should have a large Urbach energy due to variety of surface states. Yes. What you can say about it? Because I suppose that number of transition because is not limited by this 4 transition. Yes.
Yeah, I can agree. Well, actually, that's an interesting question, and I haven't thought of it, and I should think about it.
Yes,
yeah,
okay, of course. Okay. And the second question is about lifetime of your excitons. So I suppose you have measured photoluminescence at room temperature, yes?
Actually, it's not photoluminescence, it's just transient absorption spectroscopy. So we are measuring, again, the optical absorption, but with the external pump.
Oh, yes, I see. But what about the lifetime, typical value of your excitons?
Well, actually, we can estimate that, well, they are living very fast, lower than 10 seconds, picoseconds.
But I see you have large charge mobility, yes, in this system. Very, I think it could be larger than in some semiconductors, yes? Such large values of charge mobility, yes?
Well, but this is
I see this is the optical range. I see this is from optical constant, not a low frequency mobility. Yes.
Yeah.
Okay. Thank you.
Okay, let's thank the speaker again. And now this session is over, and we finished it a little bit later, so would you mind if we will start the next session in 5 minutes later, at 11:55? Thank you.
Thank you very much for your presentation. Before starting, I would like to thank organizing and program committee for giving me opportunity to present our results here at this jubileum conference and to be in such wonderful city, Samara. And personally, I would like to thank Professor Leonid Golovany for inviting me here. Okay, the title of my talk is given here, and this work has been appeared as a result of cooperation between Zhanov Institute of Semiconductor Physics Novosibirsk and three universities, Novosibirsk and Moscow State Universities and Technical University of Chemnitz, Germany. Okay, my talk will be organized as the following. In the beginning of my talk, I will give short introduction and explain our motivation. Then I will switch to our results devoted to tip-enhanced Raman scattering by aluminum nitride nanocolumns and hexagons. And I will tell about quite similar methods, tip-enhanced photoluminescence from another type of materials, gallium arsenide nanocolumns and nanoclusters, as well as dechalcogenized metal dechalcogenized monolayers. And then I will switch to new methods which our group develops, so-called gap motors. I will tell about these methods later. And I will present our results regarding molybdenum disulfide monolayers, as well as cadmium selenide nanocrystal coverage, which were deposited as monolayers, and even I will present some results concerning single nanocrystals. And at the end of my talk, I will show some results devoted to core shell nanoplatelets, where cadmium selenide is core and cadmium sulfide is a shell. And in the end of my talk, I will show some results regarding multigraphene and graphene coverage. Okay, and some conclusion will be also given. Okay, everyone knows that optical spectroscopies, especially including Raman scattering and photoluminescence, are widely used for determination of tiny amount of materials down to single molecules. And these materials these methods already found wide applications and chemistry, biology, and any field of sciences. I'm personally working in the Institute of Semiconductor Physics, therefore I'm interested in semiconductors, materials, and of course semiconductor nanostructure attracts much attention, especially semiconductor nanocrystals, nanowires, nanocolumns, etc. These materials exhibit new electronic and phonon properties, and they are also used in various device applications such as light-emitting diodes, photodetectors, memory devices, etc. But optical experiments provide actually average response from the ensemble of nanostructure, while their phonons and electron properties of just single nanostructure in general remains unknown. And this is because of extremely low optical signal of single nanostructure, which prevents determination of its properties. And therefore, our motivation was to elaborate approaches for plasmonic enhancement of optical response by just only one single semiconductor nanocrystals. How it works? So here the experimental realization of tip-enhanced Raman scattering is shown. So the cantilever of atomic force microscope is approaching the here shown by blue point. So this is actually object under investigation, an object under investigation. And important here that the atomic force microscopy cantilever should be covered by metal. And it's illuminated by laser lines through objective, and due to activation of local surface plasmon, we receive strong enhancement of Raman scattering. This is because of high enhancement of local electric fields, which appears in the vicinity of metal tip. And it's known that this enhancement of Raman scattering is proportional to the fourth order of magnitude of electric fields. So therefore, we receive strong enhancement of electric fields. So we have used, in our case, atomic force microscopy Raman setup, Hariba Explorer Nano, which is installed and working in Novosibirsk. And it is important that we can now see and detect single nano objects with high Raman yield or photoluminescence yield. And this allows us mapping single nanostructure with nanometer spectral resolution. And this is just, I would like to show the example of importance of these methods. If you click in Scholar, for example, the keywords tip enhanced Raman scattering or tip enhanced photoluminescence, you will see immediately many thousands of results. And I would like to emphasize here several important reviews which were published just in several 5 years. So the key point in this technique is so-called tip, Terz active tip. So this is actually tip of cantilever. We have used a commercial atomic force microscopy tip shown there. And covered the tip with metals. It can be either gold or silver. In order to have opportunity to change the effective the electric function of the medium, we can deposit it silicon dioxide. It gives us opportunity to change the position of local surface plasmon resonance. So, and here we would like to show how this Terz imaging is working. So, if we take, for example, aluminum nitride nanocolumns and approaches nanocolumns with metallized atomic force microscopy tip, we can see immediately strong enhancement by surface optical modes. If we monitor just intensity of these modes, we can get Terz imaging here. And important here that Terz is polarization dependent. If we take polarization along the plane of the screen, we can see that enhancement is coming from the edges of nanocolumns. If we have polarization perpendicular to the screen, then the lowest picture, then we see more or less homogeneous images. Okay, the quite similar things we did with mapping of aluminum nitride hexagon grown by molecular beam epitaxy. So here the atomic force microscopy image is shown. So just hexagon is only 50 nanometers thick and size of about 200 or 300 nanometers. So, and again, we can follow the intensity of surface optical phonons and can receive Terz image of such structure. You can even see the hexagon structure on the Terz imaging. Okay, then let's switch to tip-enhanced photoluminescence imaging of gallium arsenide nanocolumns. So this is also nanocolumns, another materials. We were able to take these nanocolumns and put it on silicon substrate. And here atomic force microscopy image of a couple such nanocolumns is shown. Then we approach again the surface of the structure with cantilever and receive the enhancement of photoluminescence here. Now then we follow the intensity of this peak and we can image can get image of this structure, and we can see that spatial resolution is actually the same like atomic force microscopy, but in addition we receive spectroscopic information about the material. Okay, the situation even more interesting and exciting when we have gallium arsenide nanoclusters grown on gallium arsenide. So we normally we cannot distinguish between the signal from the substrate and signal from nanoclusters because material is the same. The interband photoluminescence from the substrate avoid to observe any signal from nanoclusters. But interesting here that in the higher wavelengths we have additional signal which we interpret as indirect tip enhanced photoluminescence, which is related with such indirect transition shown here. And if we monitor then the intensity of this signal, we can get very nice images of tip enhanced photoluminescence, which can reproduce some peculiarities of the structure. So these craters comes from metal drops, which are actually used in so in the growth procedure. Okay, now let's switch to tungsten disulfide monolayers. So here few images of such triangular monolayers are shown. Here we can see these images with different enhancement, with different zoom, and photoluminescence spectra are shown in this figure. We can again monitor the intensity of tip enhanced photoluminescence, then peak position. We can see the area where defects come from, and the same was done with disulfide molybdenum monolayers. Again, we can zoom some area and receive photoluminescence signal, photoluminescence images. Okay, I would like now to switch to the gap mode TERS, which is developed in our groups. In this case, so the nano object is located in the gap between the tip and plasmonic substrate. It gives us additional enhancement of electric field in this area, like the same situation is existing in dimer when the nano object is located in the middle, in the gap between the metal dimers. So in this case, it can be either two-dimensional layer or such zero-dimensional materials like cadmium selenide nanocrystals or nanoplatelets, or even we can change completely plasmonic structure and take such substrate, plasmonic substrate, which was available recently. And these methods give much stronger enhancement of local field, so-called hotspot. And this strong enhancement is expected also in the gap mode TERS spectra. Okay, but plenty of question arises. For example, TERS was observed for restricted number of materials, and it's dependent on a variety of parameters. Type of materials, surrounding media, tip material, its morphology, and so on, and it gives us uncontrolled local surface plasmon resonance. Just to avoid this, we investigated the number of arrays of such gold nanodisk, determined the position of local surface plasmon resonance energy. Now we know everything about plasmonic substrate. So now, using this plasmonic structure, we try to investigate our subject under investigation, our sample under investigation. In this case, we took monolayers of disulfide molybdenum, put it on plasmonic substrate, And if you look on the Raman spectra, we can see just only quite weak black spectrum of micro-Raman spectrum. Just if you put approach the surface with plasmonic tip, then immediately we have very strong enhancement, 5 order of magnitude enhancement of the signal. Now we can monitor intensity of these modes and simultaneously can measure atomic force microscopy image and tip enhanced Raman scattering map. And if we overlap two signals, we can see that the Teragertz signal comes from the edges of such nanodisk, where the local electric field is maximum. We can enhance such area, record the spectra, again can go through this line, can determine the spatial resolution which appears 2 nanometers, about 2 nanometers. So spatial resolution, 2 nanometers, but we receive this by normal optical techniques with the wavelength 785 nanometers. So we are far below diffraction limit. Okay, we can also monitor the frequency of this mode, and it gives us, for example, this is along line 126, and we can see the changes in position, frequency position of the line, appearance of new lines, and it gives us information about the phase transformation, about mechanical stresses in these materials or sample heating. Okay, the same we did with coverage by cadmium selenide nanocrystals. We deposited monolayer of quantum dots, as shown on the left-hand side image, and measured tip-enhanced Raman scattering signal and monitored the intensity of longitudinal optical phonons from cadmium selenide nanocrystals. And we observed also the same Teragertz images as we saw for monolayer of materials. And again, the main signal comes from the edges of gold nanoclusters. We have substituted chloride substrate by plasmonic. We have substituted plasmonic substrate by chloride substrate, like it's shown here. It's represent a set of inverted pyramids covered by gold. Here shown atomic force microscopy images, which is detailed from those one. And everywhere submonolayers of cadmium selenide clusters were deposited here. Here, for example, we can see this in more detail. Small white spots are these cadmium selenide nanoclusters. And we receive the Raman signal from longitudinal optical phonons, follow the intensity, and got such Teragertz images. And despite the nanoclusters, nanocrystals are deposited everywhere, signal comes from the edges of pyramids. And according to calculations, the maximum intensity of local electric fields comes from the edges of pyramids. Therefore, the Teragertz images look like this. Okay, and finally, we saw the position where we can see just only one single cadmium selenide nanocrystals. We can pixel by pixel monitor the intensity of longitudinal optical phonons and see the enhancement, then a lowering of intensity of the signal, and two horizontal and vertical position. Okay, and this means that we were able to observe the Teragertz signal from single cadmium selenide nanocrystals with a size about 6 nanometers. Okay, we did similar things with platelets, and here the enhanced image of this area is shown. Here we can see that several platelets can be observed in Teragertz images. Platelets looks like that in scanning electron microscopy images, and Raman spectra are shown here. Okay, now I would like to say a few words about gap mode Teragertz in multigraphene and graphene. So graphene we deposited on such plasmonic structure, And this is atomic force microscopy images of graphene and multigraphene film. And if we choose such area to these films, we can get tip enhanced Raman scattering images here. We can follow intensity of different modes, DG or 2D modes, and finally we can enhance the images, look in details, and monitor the frequency position of the modes. The change of the frequency position gave us information about local mechanical stresses, which are 0.4% for multigraphene film and 1.5% for graphene. Okay, I hope that I have convinced you that we have realized Teragertz and TEPL images from different nanostructure like aluminum nitride, gallium arsenide, nanodots, nanorods, and nanoclusters. We saw TEPL and Teragertz and different kind of materials, and we got images with extremely high spatial resolution. So this is acknowledgement for the foundations which support us in different times, and thank you very much for your attention.
Thank you. Any questions, please?
I'd like to ask you, you have two subjects, material and machine. Machine, it is Charybda, if I understand. Can you compare this is machine, Charybda, with the Russian machine from Zelenograd, from NTMDT? Because I remembered maybe several years ago, it was some defense. It was theses in this organization, and they demonstrated during this thesis that Russian machines, the same machine, it is for Teragertz. How, please say several words about the comparison.
Okay, thank you very much. This is important question of import and export, of course. So I would like to say that science, it's a long-term things. Yeah? So when we started this story with Teragertz, we had close communication with Germany, and our idea was to organize mirror-like laboratory, so to have similar equipment in Germany and the same, or more or less the same equipment in Novosibirsk. And
during the last reality.
During the last, okay, I will finish. So, and therefore, I paid a lot of attention to prepare people or to, how to say, to educate people to work in this type of machine. I would like to say that in order to get a specialist in this field, at least 1 year is needed, you see, because there are plenty of parameters which should be installed to get such Teragertz images. And I would like to say that on eastern part from Ural mountains, we just only one group who can succeed to measure Teragertz spectra. And coming back to your question regarding NTMDT. Unfortunately, personally, we do not have opportunity to compare these two machines. Yeah, and there are, of course, advantages and drawbacks of any machines. So as far as I know, NTMDT has very good friendly interface regarding atomic force microscopy. But from other side, they do not have their own spectrometer like Charybda has, yeah. And they bought spectrometers from either Belarus or say any others manufacturer. So, and that's what I can say. And there are actually some paper which you obtain on NTMDT machine. So therefore, personally, I cannot compare directly. So, but there are at least 4 machines which can get, which allow to get Teragertz images.
Thank you very much. And once more question, and the last.
Thank you very much for a very interesting talk, and 2 nanometer resolution, of course, it's very much exciting. But I have technical question. How you deposit monolayers of dichalcogenide and graphene on top of your plasmonic nanostructures?
Yeah, thank you very much for your question. So, fortunately, we have our colleagues in Skolkovo or MIFI or MFT, how it's called, University, Alexander Chernov, who is producing such structures.
Thank you, and as fortunately we have no time for the next lecture, and let's thank our reporter.
Thank you very much.
And the next reporter, Professor Vasilyev, from Lomonosov Moscow State University, Department of Chemistry and Department of Material Science. Time of their presentation, exciton chirality of automatic thin sorry abbreviation, nanoplatelets with X-type stereoisometric ligands.
Thank you very much. Dear colleagues, I'm very pleased to have a talk for you. Firstly, I would like to thank the organizing committee and Professor Golovany for my invitation. So let's start. My topic, talk, the aim of my talk is show you how to create spin polarized exciton in atomically thin semiconductor without magnetic field, without magnetic impurities, and at room temperature. My talk will include chirality, synthesis, crystal structure, and interaction with right and left photon, and optical activity of our object. So the first is chirality. Chirality, very interesting properties of our nature. Chirality refers to a geometrical property when an object cannot be superimposed onto its mirror image. Here, lucky cat, here a lucky cat, and left is enantiomer, attracts customer and profit, and right pau stereoisomer attracts good fortune and prosperities. So, chirality, the most known is organic chemistry. For organic molecules, known enantiomers, which cannot be superimposable with after mirror image. So, enantiomer interact with left and right photons. Here, species of scarab beetle. So in left polarization, it have green coloration and dark coloration in right light. So chirality may be attributed to spin. We use chirality-induced spin selectivity, new effect which refer to spin or maybe pseudo-spin polarization due to electron transfer through helical potential. scatter on dissymmetric helical potential. So if electron should transfer through organic layer with chirality, electron will have a spin up or down. This new effect refers to a solution of Dirac equation in helical potential here. Dirac cats up, can down, cat and anti-cat. So when cat transfers through left or right potential, cat will have a spin. We consider exciton. We consider exciton in two-dimensional materials. One mod exciton. So we start with a well-known R2B6 compounds. When we construct atomically thin semiconductors from them, they will have giant oscillator strength, large binding energy of exciton, and our task to construct helical potential. How to create? We start with atomically thin semiconductors, commonly used layered compounds. It's very easily to prepare one monolayer. We should exfoliate by scotch tape, for example. But we need non-layered materials, non-layered semiconductors. How to create a single monolayer? It's very complicated task. So we synthesize atomically thin zinc and cadmium chalcogenides by colloidal method. We use colloidal method. Classical colloidal method have a classical nucleation. After critical size, the nanocrystal grow and grow and grow. So in special case, which we utilize, we have magic size. So nanocrystal which have a magic size do not grow. And for example, nanoplate grow by classical bilateral size and grow by magic nucleation, non-classical nucleation in normal size to surface. So we grow with use of colloidal synthesis two-dimensional nanostructures. Here the upper line cadmium telluride two-dimensional nanostructures. Here square sheet with well-faceted nanostructure. And for example, zinc selenide, triangle nanostructures, also well-faceted. So this is atomically thin crystals. Here electron diffraction pattern with point diffraction and well-described crystallographic excesses, and well-faceted with precisely corner. And our nanostructures have here image, transmission electron image, and precisely three cadmium planes we can observe. So The thickness is precisely given with only 3 cadmium atomic planes. Here, zinc selenide nanostructures, also about half of monolayer thickness, precisely half of monolayer thickness, 3 zinc planes. And here, triangular nanostructures with point electron diffraction. They are also crystal structures. These nanostructures have very narrow, exceptionally narrow excitonic bands. Here, solution, colloidal solution, pink colloidal solution of nanostructures in UV invisible region, and here luminescence. We can see by naked eye very intensive excitonic luminescence. So we use the next idea. We use enantiomeric ligand, which we use for inducing of chirality. For example, cysteine molecules or acetylcysteine molecules we have, and binding, covalent binding through phthalate group. The next is our study of chiral exciton. Here circular dichroism, difference left and right photon absorbance. So our nanostructures have a preventional absorption or left or right handled polarized light. Here red line D enantiomer and white light L enantiomer. Here excitonic transition. So here the first transition is right, spin up. Next transition spin down for white line. Here spin up, spin down. Here once more spin down, and next spin up. Here L an enantiomer of our nanostructures. In each case, each exciton line splits into level with pseudospin up and pseudospin down. The splitting is very high, about 100 milli eV, so higher than room temperature. And we can see clear high, about 2% difference between right and left photon. Usually, commonly used semiconductors interact differently only a few Kelvin temperatures, on very, very cold temperatures. Here, room temperature. So our model involve tetrahedra, cadmium selenide sulfide surface plane, 2 plane, have a set of tetrahedra, helically distorted tetrahedra. So we have a structure with screw axis, helically distorted structure. And exciton in this structure will be chiral, so spin polarized. Spin polarized at room temperature, spintronics at room temperature. And here, our control of spin polarization, we use a very, very simple method. We use dielectric screening. we use different solvents. Our nanostructure is colloidal nanostructures, so we use different solvents, and change of solvent from methanol to formamide, we can, for example, reduce G factor of a characteristic of spin polarization. So about several times we can change of G factor by changing of Coulomb interaction, so it's involve a spin-orbit interaction. So we change polarizing spin polarization of exciton. And next slide presents optical activity of these nanostructures. Besides different absorbance of left and right photon, chiral substances will rotate plane of polarization. So here coefficients of optical rotation at yellow line. So it's 20 times higher than ligand itself without our nanostructures. So we very high increase optical activity. So here we can see optical activity without special equipment. We use only two polarizers, linear polarizers. We crossed them and put one drop of our solution between polarizers. So here the light change, rotate the plane by naked eyes. By the way, the sugar, well known for our optical active substance, we need about 10 centimeters length of sugar to rotate the plane with the same angle. So it's very interesting object. My co-authors, my postgraduate student, and the work was funded by Russian Science Foundation. And here, chiral two-dimensional cat. This is a very nice cat, the same nice cat as our excitons. Thank you.
Thank you very much for very interesting and nice presentations. And any questions, please?
So I think we discuss it at coffee break. So with pleasure answer your questions at coffee break.
But let us to enjoy what color anti-cat has if cat is orange.
Anti-cat is green, so I think.
Thank you very much. And then let us thank our reporter once again.
Thank you.
And the next reporter, Professor Golovany from Moscow State University, Moscow. The type of representation, up convection in carbon-insulated zinc sera, quantum dots in liquid crystals matrix. Please.
Okay, thank you. Well, this work was done by joint efforts of two scientific groups from Faculty of Physics, Moscow State University, and Institute of Petrochemical Synthesis, Russian Academy of Sciences. And I think I need not to explain how semiconductor quantum dots are important, and we could hear yesterday plenary talk, and just now we have listened to reviews of quantum size semiconductors. Well, the thing is, quantum dots are extremely promising, and but if we have a kind of device based on quantum dots, we have to some kind immobilize them, because solution is not the best suspension. So the solution is not the best medium for practical use. Well, and in our work we used smectic liquid crystal polymer asymmetrics, and the thing is, it allows stability and homogeneous distribution of quantum dots, and during the introduction, during the embedding quantum dots into the polymer, hydrogen bonds in mesogen might be responsible for liquid crystal formation. Does it work? No. Sorry. Is substituted with ionic bonds with quantum dots, and in this way, very stable composition is formed. Well, and as one can see, the embedding of quantum dots is the quantum dots are embedded more orderly, and in this way we could obtain rather high concentration of the quantum dots, and this is important for formation of light emitting devices, or maybe even lasers in future. Yeah, and we employed both core type and core shell type cadmium selenide quantum dots, and as one can see, there are the left panels are photoluminescence spectra of quantum dots, and dynamics, and in core type quantum dots there are two broad bands. The right with higher photon energy is exciton luminescence, and the broad with maximum at about 1.7 electron volts is a defect photoluminescence caused with some selenide vacancies, and as one can see that efficiency of quantum dots embedded into symmetric liquid crystal polymer is a little bit higher than in case of quantum dots in amorphous matrix, but employing co-shell structure with the shell of broadband semiconductor is very useful, and it allows the defect band to be suppressed, and you can compare the left panels with the right panels. These are for co-shell structure, again in liquid crystal upper panel, and in amorphous polymer, the bottom panel, and one can see that in liquid crystal polymer, the band, the excitonic band, is shifted to the red, about 100 milli electron volts, and this is result of closely packed quantum dots and resonant energy transfer from quantum dots of less diameter to quantum dots with high diameter, from quantum dots with higher band gap to quantum dots with less band gap. Well, typical absorption spectra, and demonstrating the exciton peak, and typical photoluminescence spectra. His excitation is at wavelengths of 532, and we can see a rather broad band, and the broadening is caused by distribution of size distribution of the quantum dots, and size distribution, and of course distribution of band gaps in these quantum dots. Well, but in our experiments, we found that the films with embedded quantum dots demonstrate effective. Effective is not the best word, but very bright luminescence, even if they excited by infrared radiation. So we employed chrome forsterite laser, 1.25 micrometer wavelengths, 80 femtosecond in pulse, and in this case, both for co-shell quantum dots and co-quantum dots, luminescence spectra are close to spectra obtained with green laser excitation, and the spectra demonstrate similar broadening, and in co-type quantum dots, similar defect band. And that's why we tried to find out what this upconversion mechanism is. And I'd like to say that photoluminescence was not excited with continuous wave radiation of the same laser of the same power. Well, let's indicate on nonlinear absorption mechanism of photoluminescence formation, and this plot shows how this photoluminescence spectrum depends on position of focus spot on that sample. We employed 15 micrometer film and shifting the laser spot across the film results in variation not only photoluminescence intensity but the position of maximum. You can see that the dashed line is an eye guide. The position is shifted to the red side when the focus is inside the film or below the film, and this is a result of light reabsorption. Well, and I'd like to show that energy of excitation photon is much less than photoluminescence, and the energy of photoluminescence photon, and in this case we can work with 3 photon excitation. Well, to prove this effect, we carried out direct measurement of the nonlinear film transmission with the same femtosecond laser, and the plot depends the plot depends shows the dependence of this value transmission at low laser power and transmission at higher laser power squared, depending on squared laser pulse intensity. And in this case, this plot allows us to find coefficient of 3 photon absorption, and surprisingly, this coefficient for the nanocomposite consisted of about 9 volume percent of quantum dots. Is of the same order as as 3 photon absorption coefficient for bulk cadmium selenide. Cadmium selenide materials is concentration is less, but the signal, the efficiency is the same. Well, and here are dependencies of photoluminescence on of toluene solution and cadmium selenide zinc sulfide quantum dots on laser power, and we found that the dependence of photoluminescence signal at different wavelengths is approximately cubic on laser power at low laser power, and for higher power it tends to be saturated, and their tendency is more pronounced for less photon energy. So with increase of power, there is a reshaping of the photoluminescence spectrum. And you see the red wing of the photoluminescence saturates at lower power than the blue wing. And we can explain this fact with the energy transfer from, again, energy transfer from small quantum dots to quantum dots of higher diameter. And in this case, at the same laser power, the diameters of high diameter are highly populated than quantum dots of small size, and this should be fast process, and again it's very likely is resonant energy transfer process. So that's I think I have to conclude now. So that's my conclusion, and I would like to acknowledge Russian Science Foundation and my colleagues for fruitful discussions.
Thank you very much. Any questions, please?
Victor Sokolov, Photonics. Many questions, but I would like to ask only two questions. First, what is the quantum yield in upconversion when you excite cadmium-selenium dots by 1.25 nanometers in percent? What is the quantum yield? And the second question is, the concentration of quantum dots up to 30–40% is very high. Do you have the problems with agglomeration of quantum dots?
Yeah. So, for the first question, let me say that it should be measured accurately. It still should be measured, because I won't give a precise value. For the second question, I believe that employing smectic liquid crystal polymer is the way to avoid agglomeration, because the quantum dots are to some extent ordered, and this picture gives a hint how they ordered well. Of course, very rather idealized, but something like this. And in this case, we don't have agglomeration, in contrast to amorphous polymer.
Any question?
Thank you for a nice presentation. I have two questions. what is the role of this nematic liquid crystal polymers in this study? And did you also, second question, did you also carry out this size distribution of the quantum dots in your samples using some time studies or what? Because we are explaining this some effects in terms of the resonance energy transfer from the quantum dots of different sizes, small sizes to larger sizes. Thank you.
Yeah. Sorry. There is you can see the size distribution. That's obtained from analysis of TEM images. Well, I'd like to say that this figure is not complete because there is a size distribution of core shell quantum dots, and of course the most important impact is from the core, and it has its own distribution, and I didn't show it, but again it's about it's again about 2 nanometers. Well, and sorry, the first question was
the role of this liquid crystal polymers. Are you using this as a host simply, or is it playing some important role for this 3-photon luminescence studies?
Well, 3-photon luminescence is caused by nonlinear absorption into the quantum dots. And the polymer allows us to immobilize the quantum dots.
You are using it as a host.
Yeah.
Instead of this, we can use some other polymers like polymer composite like PDI. And
yeah, but it's again to your question. Another polymer wouldn't allow us to reach high quantum dot concentration. Well, in fact, we can see if we speak about impact of the matrix. We can see anti-Stokes Raman scattering at frequency of the polymer. It's rather high efficiency, but in this case it's not quantum dot, but polymer frequency.
Thank you. I guess that the other questions will be discussed in course.
So, dear colleagues, we continue our session, and the next talk will be presented by Professor Zimnikov from Yuri Gagarin State Technical University of Saratov, and you are here, so welcome. And the talk title, Fluorescent Amplification in Laser Pumped Random and Homogeneous Fluorescent Media, Their Fundamental Limitations. Yeah. So.
Okay, thank you. So I would like to thank the conference organizers. This is a traditional beginning for possibility for me to join this meeting and to sightsee this nice city of Samara. So, and the title of my talk is presented here. So, fluorescent amplification, laser pumped random and homogeneous fluorescent medium, fundamental limitations. Okay, so this topic is closely related to the problem of random lasing in disordered media. So this idea was pioneered by Professor Litokhov more than maybe around 50 years ago. But the strange situation, it appeared a long time gap, more 20 years gap between this key paper and the first experimental observation of a random Wasing effect. So, and the idea of random Wasing is very simple. So we have a random medium with high scattering properties, which is saturated by a fluorescent component with a high quantum yield, and it is pumped by a pulse periodic laser light, and at certain pump energies we can observe the narrowing of emission spectrum. So, and the transition to spontaneous fluorescence to this random Wasing is very narrow in the energy scale. But the important fact that under further increase in pump intensity, we have no changes in spectral properties. They are very stable. So, and the simple qualitative model for this process is presented here. Oh. Oh, sorry. So, with one, so, and actually, this is not a pure Wasing phenomenon, is rather a superluminescence, because multiple step amplification of spontaneous radiation. And the interest to this system was grown up in early, in the beginning of this century, but in this time it's gradually fall down, but interest remains, because this system could be useful for development of novel technologies for diagnostic of random media, diagnostic of superluminescent system, and so on. And to find the position of this system among other light emitting system, light amplification system, I tried to present the diagram which illustrates the relationship between different systems in terms of beta factor and characteristic time, residence time of fluorescent photons in the medium. So we can see here the pure gas laser, cavity-based system, semiconductor lasers, and non-cavity random lasers. This is a yellow circle. And we can see that the beta factor is around 0.1, and dwell time is around tenths of femtoseconds. For other systems, we see here the sufficiently larger dwell times of fluorescent photons in the medium. And the idea was to establish the relationship between the dwell time and spectral properties, and find the possibility to improve the ratio, the spectral quality of a random laser, and so on. So, and in our experiments, we use the typical laser dyes, rhodamin and DCM. So, here is the specification of fluorescent systems. And the scattering matrices the laser densely packed titanium particles with high scattering efficiency. In DCM-based system, we also studied the natural scattering matrix appearing in DCM solution due to limited solubility of the DCM and ethylene glycol. So I will provide some comments about it. And pumping, this is a green line of green laser line with a wide range of pulse energies and with the duration about 10 nanoseconds. And we used focusing of laser light on the samples, and so we can change the pump intensity in this range from megawatts to gigawatts per square centimeter. So, and the question can arise, what's the reason to study this well-established and well-defined system, defined in these emission properties? But I will try to ask this question because, as I hope, the technique which we use to analyze the emission spectrum, depending on the pump energy, could be useful for other applications. Okay. And the idea of this spectral analysis technique is based on the so-called probabilistic model. We consider the light emission due to stimulated emission acts. Typically, the birth of the photon packet is carried out due to spontaneous emission, and this photon can travel due to random walks through the medium and obeys the sequence of random simulated emission acts. So, in framework of this model, we introduce a specific parameter. We call this parameter is fluorescence amplification factor. Is gamma. Gamma. It depends only on the wavelength. It doesn't depend on the pump intensity. So, and we can analyze the behavior of this parameter, covering from the set of spectra, set of emission spectra, and we can interpret its behavior in terms of ratio of dwell time or residence time, average residence time for photon, for emission photon in the medium, to the characteristic time of amplification, which is defined by average distance between two sequential emission events, spontaneous stimulated emission. So this model is valid only in the case of stationary emission, but as we obtained in simulation, typically at high pump intensities for this system, where this quasi-stationary states is reached only in the beginning of acting pulse, and we can suppose that the emission system is in quasi-stationary mode, and we can describe it in terms of statistical distribution of photons. Actually, we deal with the probability of photon to emit at certain wavelength by normalization of emission spectra to unity. So, and this slide illustrates the processing of the emission spectra. So we have at the left panel row initial emission spectra at various pump intensities. So we have see here the formation of a random Weizen peak due to increase in pump intensity. The right panel is after renormalization of emission spectra. So next slide shows the nonlinear transformation of normalized spectra. And after this, we subtract the background from all spectra. And finally, we arrive to the next form. This is a logarithmic function of fluorescence emission factor, with one is on the right panel. It varies pump intensity, and we can see that it actually doesn't depend on pump intensity and characterize the behavior of the system. And this is a composition of two factors. This is a spectral dependence of stimulated emissions cross-section, and the distribution of the excited dye molecules across the vibrational levels. This one is totally recovered emission factor for DCM, solid DCM dye. And here we can see analysis provided with DCM with factors. This is a rhodamine-based emission system. So I'm sorry, I see here a misprint. The green colored, not red colored points and curves is the rhodamine solution in titanium matrix. So the emissions factors belong to the left vertical axis, and initial spontaneous emission spectra are fit to the right axis, right vertical axis. So we can see here the transition from one matrix to another matrix shows causes the red shift of emission factor, and we can see here the shoulder, long wavelength shoulder. So, and presumably this is due to sufficiently large effective area of a small-sized matrix, 25 nanometers, compared to 100 nanometers matrix. So, because of large surfaces. And next slide is the same dependencies for DCM based matrix. This is only a very interesting system, the CM, because we have here any matrix, the matrix is formed by the nanocrystallites or microcrystallites of DCM. And we have here strong scattering. So the left panel is collimated transmittance of a DCM solution at different molar weights of dye. The right panel is the characteristic extinction length for pump intensity is a green points and green curve, and for emission maximum. So we see here that strong scattering in this system. So this is due to many micro and nanocrystals of DCM This is scanning electron microscopy of sedimented particles, DCM. This is and diffraction X-ray diffractometer show the expressed crystallic structure of these particles. And left panel shows the result of interpretation of these scattering properties. So depending on the mass fraction of DCM solved in ethylene glycol. So typically this is a mis-scattering, and so we have analyzing this data, we see that propagation length between scattering events in such system is very small. And because we have strong elongation of propagation paths, and typically we estimate that working concentration of DCM, where we have estimated the average propagation path, mean transport free path, about 50 microns. It's very small. And it is very interesting to compare this system with classical cavity-based system. So, because at high pump intensities we have the line width of emission is determined only by the amplification with improvement factor. So we provide some simulations and find for with two shapes of should fall as on power off with depending on the number of scattering, average number of scattering event, or the same the dwell time for photon in the system, and the law of decrease is typically parabolic. We can see here. But comparing with line width of cavity-based system, typical system, we can be based on the Shaw-Towns expression for the line width of cavity-based laser, depending on the set of parameters. And the parameter with the parameter indexed as RT is a round trip time. We actually define the dwell time of photons in the cavity for this system. And typically, because we have the inverse quadratic law in dwell time, and additionally the output laser output power also increases with increasing dwell time. So we can see here for such system much more strong decay in compared to our system with no cavity, with only random walk of radiation in the system. And we have modeled using Monte Carlo simulation. We modeled the average propagation path divided by the system size, and we can see if we if we increase the transport mean free path, it seems that average time should increase, but it is actually no, because we have a lot of competition between various factors, and with competition limited the average dwell time. And previously we have shown that amplification length, or the distance between two sequential acts of two stimulated emissions for random propagation in the system. It doesn't depend on the system properties. One system is oversaturated. It depends only on size of emission area, because due to speckle modulation of pumping radiation inside such system, typically the system depends on the with length depends on the average size of emission area and the radiation loss factor, which is defined with emission from these local emitters. So we have here two publications regarding this point. And finally, I would like to say that any attempts to move random Lorentz thing towards the classical Lorentz system, I think can be not very successful because the limitation due to random walking of propagating light in the diffusion mode. But I think the introduction of this amplification factor can be useful for the various diagnostic purposes because it very sensitive to metrics. So it means that it's very sensitive to interaction of fluorophore excited molecules with solid with the surfaces, with solid phase, with condensate phase, and so on. And I think it can be applied in addition to other diagnostic technique. Oh, okay, so thank you for attention. Mm-hmm.
Thank you very much for your interesting and fruitful presentation. So, colleagues, some questions? Yeah.
Thank you for your talk. Maybe one simple question. Is there a difference between random lasing and amplified spontaneous emission? So or it's the same?
Okay. So this term appeared in early 90s of the last century. And typically, what's the lasing? If we consider the abbreviation, late amplification due to emission, stimulated emission. So absence or presence of cavity is a secondary part of this term. So I think this effect can be interpreted as a lasing. But if we more strictly, because no cavity, no spectral selection, no wavelength selection like in traditional cavity system, because we have here the set of local frequencies, very narrow frequency interval, peaks of emission, and we provide the cutting of emission spectra inside these intervals, okay? And because we have a great quality factor in this system, so I can show the slide with B factors and dwell time. Okay, but if so, it depends on you.
Okay, short question. What is the difference between lasing and superluminescence?
So we have here in this system, we have oversaturated excited state. No optical feedback. So and typically, I think this we can compare in such a way maybe superluminescent laser diode and laser diode super light emission diode. and the laser dye, this cavity. Cavity no, is not very fine, this high fine is not, but due to larger amplification, we have here emission.
So thanks again. Unfortunately, we have no time for any more questions. So please ask it when we have free time. So thank you again for your nice presentation. And the next report will be presented by Professor Weiner. Yeah. Please, welcome. And the report title Study of Colloid Nanoparticles in Aqueous Solution by Ultramicroscopy and Dynamic Light Scattering. So please, welcome.
Okay. The development of nanophysics and nanotechnology makes necessary to develop effective methods for diagnostics of nanoparticles, especially in the case of nanoparticles in water aqueous solution, aqueous medium, and also especially on the single particle level. Why? Living organisms cannot exist without water, which is their most important component in aqueous solution. And one of the most used and promising technologies for synthesis of nanoparticles is colloidal synthesis in aqueous solution. Studying nanoparticles at the single level makes possible to exclude the ensemble averaging which inherent to ensemble of nanoparticles. Okay. Usually, people used for diagnostics and characterizing of nanoparticle electron microscope due to very high spatial resolution. But electron microscopy have several significant disadvantages. First, inability to carry out measurements in aquatic environments, undesirable effect on the object under study, inability to carry out remote measurements, in particular in vivo measurements in biological objects, complexity and long duration of the measurement procedure, a long amount of preparation is required, high cost and low availability of equipment. So it is interesting to compare the possibilities of electron microscopy with optical microscopy. The main advantages of optical microscopy is high efficiency, simplicity and short time for measurement, low effect on the object and the study, possibility of studying biological objects in native conditions, possibility of remote measurements, high and ultra-high temporal resolution, information content, including the ability to obtain spectral information, relative simplicity, low price and availability of equipment. No need to lengthy user training. So, in my talk, I will tell you about the developed by us high-sensitive optical microscope for diagnostics of small nanoparticles, and I will demonstrate results of studies using this microscope. Outline of my talk is the following. Schematic diagram of the developed laser light sheet ultramicroscopy I will show you. After that we will discuss nanoparticles and the study. I will show result of comparison studies of the same nanoparticles using electron microscope and our microscope. We'll tell you about nanoparticle trajectories analysis and several words about fractals. The result, after that we consider the result of studies of nanoparticle solutions and brief discussion and conditions and conclusion. Okay, it is widely believed that optical microscope cannot be used to observe very small nanoparticles which sizes much smaller than wavelengths. It is not true. Diffraction limit doesn't allow to observe structure of small nanoparticle, but to visualize small nanoparticle, even have size of one molecule, is not limited by diffraction limit. A good example is clear night. As a clear night condition, we can see stars. The angle size of the stars much smaller, many orders smaller than diffraction limit, but we will see this size. And this is example of our measurements. With our microscope, you can see the nanoparticles on the surface of glass plate, ultra pure glass plate. The main reason why at normal condition we cannot see too small object is low signal to noise ratio. As a rule, the parasite scattering from another particle, from defects on the plates and so on, reject the possibility to observe such. To obtain very clean glass plate, it's very difficult. We need very long procedure to clean, but very easy to obtain clean solutions. If you have not clean solution, if you have not good filter, you can use filter procedure several times, so many as you need, and you will obtain a very clean solution, liquid. For example, one easy to obtain 1 cubic of solution with only several nanoparticles at normal conditions. So we developed high sensitive ultramicroscope for observation of nanoparticles. In principle, ultramicroscope was known in physics more than 100 years. But to use such microscope, you need very bright source of light. In principle, laser is source of very bright light. But laser is characterized by special coherence. As a result, when we used laser as a source of light to visualize nanoparticle, we will see speckle picture. Speckles from additional particle, from windows, from scattering, from micro objective, and so on. So we use special random phase demodulator and to remove special coherence of the laser. As a result, you can see that using our microscope, we can detect very small nanoparticle up to 10 nanometers size with good signal to noise level. And another condition to obtain high value of signal to noise ratio, we use so-called light sheet elimination. Light sheet, it means that light in our case look as a plane, thin plane. As a result, scattering before and outside of this plane not include in signal. And as a result, you can see a very good signal to noise ratio. Okay, what information can we obtain using the optical microscope? We cannot to see structure in principle, but we can determine the size. For this, we can analyze the Brown motion of these nanoparticles. And there exists nanoparticle trajectory analysis, which allow us to determine the hydrodynamic radius of nanoparticles. You can see visualization of nanoparticles, laser here. This is, after that we determine the centrum of this nanoparticle, calculated the Brownian motion trajectories, and you can see these trajectories. And after that we can determine the guided dynamic radius of these nanoparticles. As a rule, when we perform measurements in liquids, you have convection. In principle, you have to use very strong temporal stabilization, but it's made your setup very complicated. But there is a theorem: if you have a closed volume of the liquid, you can find point where convection is absent, because convection you know all direction, and you can find this simply moving qubits. Certainly, if you find this point, the convection will not zero because condition change. But for measurements, it's enough. But also you can use additional analysis using the computer. And you can see result of our measurements here. This is, in this case, we have the laser beam not. Okay, as a result of convection, we can see that centrum of particle is not in zero. And you see this convection tracks. But after use the computer, very simple procedure for students. You can remove this contribution, and the centrum of this particle will in the center. Okay. To check the possibilities of our microscope and to demonstrate these possibilities, I will show you the result of measurements of silver nanoparticles in water. In principle, this is colloidal solution. We know that colloidal solution is very temporal stable, usually, especially for many years. This solution can be in the table, and we cannot to see the redispersion of components. But when we check this silver solution, you can see, the average size of 10 nanometers. We know about this, and some distribution. Result of our analysis, we have single nanoparticles, we can detect double nanoparticles, and we can detect three nanoparticles. This is not stable clusters. Maybe they disappear. Maybe this is pure electrostatic forces. I will show you, but nevertheless, it demonstrates that our microscope can analyze these distributions and to разделять contribution. Okay. Now, several words about objects, nano-objects under study. We study nano-objects which is interesting for biological purposes. This is aqueous solutions of lanthanum fluoride and lanthanum phosphide nanocrystals doped by neodymium and praseodymium rare ions, and nanocluster based on them in quantum solution. Why we used this nanoparticle? Why they are interested? First, optimal sizes, 5 to 25 nanometers, narrow spectral absorption and emission lines, possibility of use in the first and second optical windows of biological tissue transparency, and in UVC region. Long lifetimes of excited states, as a result, possibility of detuning tissue autofluorescence, high luminescence quantum yield, high photophysical and chemical stability, low toxicity. Technology of nanocrystals synthesis has been developed. Technique for doping this nanocrystal with rare ions also developed. Applicability of nanoheaters, and we can use these nanoparticles as nanoheaters and nanotemperature sensors. Okay, we performed comparative studies of these nanoparticles in order to compare possibility of optical microscope and electron microscope. And on the left you can see result of electron TEM images of nanoparticles and of Lantan-Ftor. Okay, yes, I forgot. This is different nanoparticles. Left is Lantan-Ftor 3 nanoparticles. Right is Lantan-Pro4 nanorods. And you can see that we can see clusters of these nanoparticles in both cases. But we cannot to say what is the reason of this clusters formation. Maybe it's due to усыхание, drying. Maybe there's a lot of drying of water solution in the case of preparation of this sample. One of the significant problems of colloidal solutions, which greatly hinders their use, is for medical purposes in particular, is clustering of these nanoparticles during the drying and during the synthesis. And one of the goals of our study was the investigation of the process of aggregation of synthesized colloidal nanoparticles in aqueous solutions. Okay, how to characterize such clusters? Usually for this purpose use the concept of gyration radius. What is the gyration radius? This is a radius of inertia, which are determined by by this new formula. For clusters which consist from several nanoparticles, this formula can be used. And this is example of cluster and his gyration radius. And here, distributions of gyration radius are calculated based on these 10 images. This is primary nanoparticles. They also have distribution of size. And this is distributions of gyration radius, which characterize these clusters. Okay. And here I show the results obtained with electron microscope and our result. We see that optical microscope show clusters which more size. What is the reason why the hydrodynamic radius is more than gyration radius in our case? To answer this question, let's consider briefly the so-called fractal geometry. Usually clusterization of colloidal nanoparticles are described in the frame of the so-called fractal geometry, fractal model, because we practically haven't another models. This model is very good developed on the mathematical level. And you see examples, typical example for fractal structures. For example, this is gold nanoparticle. This is theoretical examples. Okay. Fractal structures characterized by fractal dimension. If fractal dimension is 3, this is a normal particle, density particle. And if fractal dimensions very low, for example, close to 1, this practical look like this line. If fractal have the value between them, you will see different structures. For example, for these fractal dimensions, you will see. So most cluster which observed in colloidal solution have fractal dimensions about this value. Okay. Now we performed to explain this dependence and to check if our clusters have really described by fractal model. We performed model calculations. We modeled clusters of different fractal dimensions and calculated both hydrodynamic radius and gyration radius. And as a result, we can see next situation. If the ratio R gyration to hydrodynamic radius is more than 1, we have seen that R gyration distribution of gyration radius have more sizes than distribution of small sizes than distribution of gyration radius, of hydrodynamic radius. If this ratio is smaller than it is, we have another situation. And in the case, this relation should be next. But we have opposite situation. It means that in our case, clusters cannot be described by fractal model. As we know, nobody checked experimentally the fractal nature of clusters. Usually people say, okay, cluster looks like fractal, we will use fractal theory. And never check experimentally, it's true or not. We can use fractal model or not for such calculation. Our result shows that not. For case of our particles, maybe for another particles, we have another result. Okay. Our setup our microscope allow to check real temporal stability of colloidal solution. We do it. Okay, I will change. For example, we control stability of colloidal solution in different part of cuvette. We can see distribution in upper and low part, and we can see that, okay, I need several minutes, but huh?
1 minute.
Okay, the more important result. We have distribution of sizes of nanoparticles. From the theory, we know that small nanoparticles is described, the intensity of the scattering is described by Rayleigh scattering. For more larger nanoparticles, mis-scattering. For intermediate, we will see, for Rayleigh scattering, we have 6 dependence of intensity in 6 power, in the case of quadratic dependence. But in experiment, we have seen broad distribution of sizes, but practically the same intensity. What is the reason? Is the Rayleigh scattering is not true? For these purposes, we performed, we changed our setup a little, perform measurements, and perform model calculations. For this purpose, we used the so-called Rayleigh-Ganz scattering. In the case of single nanoparticles, we use Rayleigh scattering. Big nanoparticles, mis-scattering. But if we have collection of small nanoparticles, cluster, in this case, it is necessary to use Rayleigh-Ganz scattering. Rayleigh-Ganz scattering In the case of relay scattering, all phases, all atoms are the same. In the case of relay gun scattering, the phase is different, but there is a distance between particles. And we perform model calculations. And we can see two experimental dependence and dependence which we measured, which we calculated in model calculation. They are practically coincide. The difference is the noise level of CCD camera. So they developed, and we can compare with very widely used DLS method. People used for analysis of nanoparticles DLS method. And this is the result of our studies and DLS. In the case of our studies, this is electronic microscope results. We have 2 Gaussian. In our case, we have also 2 Gaussian, more broad. In the case of DLS, we have only 1 Gaussian. So DLS method is an average method, and significant part of information about nanoparticles is losses. In our case, not. Okay. Thank you.
So thank you very much for your nice presentation. Unfortunately, we have no time for questions. Absolutely have no time for questions. So, no comment, yeah.
Be careful with the word fractal, because the father of fractals, Benoit Mandelbrot, will be not agree with you, because the main idea of fractal is a self-similarity, самоподобие.
Yes.
And I'm not sure that your clusters has this property.
The main result is that fractal model is not working in our case. This is the result.
Yes, thank you again. So, unfortunately, I absolutely have no time. So, thank you again. So, for this nice and very good report. So, the last one, but not the least. So, the report from Dr. Sokolovskaya. About the enhancement of Raman scattering efficiency in suspension of submicron particles. So let's start.
Hello, everyone. Yes. Okay. Hello, everyone. Thank you for the organizers for inviting me at this conference. And my topic is similar to 2 previous talks. I will talk about enhancement of Raman scattering efficiency in suspensions of submicron particles. They are high scattering media. What is the motivation of my study? We would like to find new radiation sources always, and we would like to make a remote identification of substances. The main property of radio medium is as follows. If we consider medium without scatters, the photon path length is determined by the width of our medium. And if we add scatters to this medium, the photon path length increases due to scattering. Thus, the scattering medium can be considered as a combination of an active medium and a resonator. In a convenient resonator, we have scattering, but clearly backward scattering. And in this case, we have scattering at some random angles. And if our medium is, for example, Raman active or luminescent active, we can obtain an increase in the signal from the medium because of the increase of light-matter interaction. And it is really possible to get significant increase in light scattered intensity compared to the incident one due to return of photons to the medium due to light scattering. the less generation in such cases is possible, as it was said, but for this we require fast and intense optical pumping that is not so convenient to study, for example, biological media that are sensitive to heating. Let us consider the two types of effects that appear when we talk about controlled light elastic scattering. First, there are incoherent effects. It means simply the photon path lengths increase due to multiple scattering. This effect we can use in solar energy applications. For example, take a material, add into it scatters to alter its absorption spectrum to the required one. Or it was experimentally shown for the ensembles of nanowires, for semiconductor nanowires, that the efficiency of Raman scattering and second harmonic generation increases in them comparing to the bulk, to the signals from bulk, from bulk substrate of these nanowires. The second is coherent effects, and there include random lasing and big localization. It is coherent backscattering that occurs when we have two light paths. There are two light paths that are time reversed to each other, and they interfere because the path length of photon between the first scatter and the last is the same. And if the phase difference between these two waves are zero, they interfere constructively, and it results to a narrow backscattering cone. And the intensity maximum of this backscattering cone is 2. On this picture, you can see the emission from random laser based on barium sulfate powder. On Raman frequencies and the stimulated Raman scattering amplified by elastic scattering in barium sulfate is reached. The research plan was as follows. We studied the effect of light path increase on efficiency of Raman scattering. To what extent the signal can be increased due to the photon path length increase? We have performed both laboratory experiments and numerical simulation. We have produced series of samples representing high scattering media with different volume fraction of scatters. We have measured their spontaneous Raman spectra by Raman spectroscopy with employing wavelengths of visible and infrared range. We performed measuring photo dwell time in samples from the field cross-correlation data measured in optical heterodynamic technique. I will show it later. And the goal is to analyze the results and conclude if there is a correlation between photo lifetime in suspensions and Raman scattering efficiency. Numerical simulation we have performed through Monte Carlo simulations. It is a common method to simulate light propagation in turbid medium, and in Monte Carlo simulation you can easily vary the size of scatters, the wavelength of radiation, and directly calculate different intensity distributions, backscattered, forward scattered, and you can calculate the energy density in the sample even time dependent. And of course, we will compare the results of simulation and experiment. Okay, our Planck samples were suspensions in dimethyl sulfoxide. This matter is characterized by large Raman scattering cross sections, and the scatters were the commercial particles of titanium dioxide and the lithium gallium phosphide particles that were obtained by mechanical mining of gallium phosphide wafers. The mean size of titanium dioxide particles is 0.5 micrometers, and the size of gallium phosphide particles was 3 micrometers. The plot wavelengths are shown on slide, and the scattering properties of our particles at these wavelengths are also shown. We have investigated a wide variety of volume fractions shown. And this is the absorption spectrum of gallium phosphide, and we are showing that the maximal absorption coefficient in the gallium phosphide, due to maybe impurities, is less than 100 inverse centimeters. This is optical heterodynamic scheme, and we register the cross-correlation function between the incident field, the incident femtosecond pulse, and the scattered light, the time dependence of the electric field of scattered light, y cross-correction function. Because if we calculate from this data the squared model of cross-correlation function, we conclude the reflected power from the signal as a function of time. We obtain experimentally time distribution of photons. Yes, and we have performed consistent connected Monte Carlo calculations, as I said before, and the reflected signal is the sum of specularly reflected signal and the signal from scattered medium. It is the transfer function H, and P0 is the incident pulse. It's the illustration because it's the illustration of that Monte Carlo is close. Monte Carlo solutions is close to diffusion equation solutions, but Monte Carlo is good at considering small order scattering. That's why we compare our experimental results not with diffusion equation solution, with Monte Carlo solution. These are types of supposed backscattered photon dynamics. If we see the dependence of backscattered power from time, and this dependence will decay exponentially, then we have diffuse photon transpons, and we can calculate photon diffusion coefficient from this decay. Or if the diffusive light transport is absent, we have discrepancy between diffusion approximation of reflected or transmitted light of time. We have discrepancy. We can consider time-dependent diffusion coefficient of photons and make some conclusion about non-diffusive photon transports. About some interference effects between scattering waves. We performed Raman studies of our series of suspension and performed the Monte Carlo calculations for the same parameters. This is Raman spectra of dimethyl sulfoxide that will be altered in presence of scatterers with varying volume fraction. There are the parameters of our experimental setups. We employed continuous radiation in near infrared and pulse radiation in visible parts of spectrum. These are the results of cross-correlation function of fields measurement for different concentration of scatterers. We see that cross-correlation functions with scatter concentration increase, its intensity increases, the backscattered intensity increases, and the maximum order of scattering is decreases. And also we have some non-diffusive light character propagation for suspension with scatter volume fraction about 10%. We tried to make exponential decay fit for these curves, and the exponential decay is not valid for the most dense suspension. Thus, we concluded that there are some interference effects at such large volume fraction or concentrations of scatterers in diameter sulfoxide. These are the results for gallium phosphides, and the diffusive light transport was observed only for the most dense suspension. For less dense suspensions, we probably observe the effect on absorption in gallium phosphide particles, and thus the propagation of light, the backscattered light dependence on time, is non-diffusive. From these dependencies, we obtained the dependency of mean photon line times and the backscattered power exponential decay times from bound volume fractions, and we found it that the mean photon lifetime in suspension decreases with volume fraction of powder. It is connected with strong ice scattering and more fast reflection of light by suspension. Nevertheless, the dwell time of photons is much larger than the duration of femtosecond pulse, that is 60 femtoseconds, and the mean photon lifetime is about 2 picoseconds. Okay, there is shown deviation of diffusion coefficient for the most dense charge suspension from the exponential fit. Then the Raman studies, we have performed some simulation of the backscattered Raman signal from Rothschild suspension for different particle sizes and for different volume fraction of scatters, and we have tried to find the optimal concentration of scatters and their size to obtain maximal increase in backscattered Raman signal due to multiple light scattering. And we have found that the optimal size of scatters is about 200 nanometers, and the optimal light volume fraction is, the optimal scatter volume fraction is about 1,000 part, and these effects are not described by mere resonances. There is a scattering cross-section dependent from particle diameter. There are the results of Raman scattering measurements of pure diameter sulfoxide and diameter sulfoxide with scattering particles. We see that there is an increase in Raman intensity while we add scattering particles in our suspension. This is the example of the convolution of Raman peaks that we have performed, and these are the dependence of the Stokes signal on laser power. We show that it is linear, therefore there is no heating of samples. Okay, this is the comparison of the simulation and the experiment. In the simulation, we have the maximal signal increase of 6, and the experiment is qualitatively coincides only with simulation. We think it is because for that large volume fractions, there is some interference effects appear, as we have shown in optical heterodynamic of photon dwell time measurements. So nevertheless, for 552 nanometers, we have qualitative agreement in Raman signal growth in experiments and simulations. Okay, and this is for CR symmetric stretch and antisymmetric stretch band of the Massot Raman modes. We have the same situation. The increase in Raman signal, backscattered Raman signal in the experiment is present, but it is non-monotonic and large scatter volume fractions. And the increase of Raman signal that we obtain in experiment is 2 maximal 3 times, and it is similar to the maximal increase in coherent backscattering process that is twofold. For gallium phosphide suspensions, we have the result that the absorption on impurities, as we suppose, that is, however, less than 100 centimeters inverse. This small absorption prevents our media to increase Raman signal, even at large part of volume fractions. These are the conclusions. We observe diffusive and non-diffusive light transport in suspensions. So we see that Raman signal increase in turbid media is possible in specific range of volume scatters, but this increase is not so large as predicted by Monte Carlo model, by diffusive model, when scattering acts are independent.
Thank you for your attention. So if you have only one short question, so please ask it. So I think that our brains is now full of information, so thank you again. And thank you all for this nice session.
Thank you. And that was the last talk of our session, and now the session laser spectroscopy and diagnostics is successfully completed. And let me thank all participants for their extremely interesting talks, and we have a year to think of all these things, and I hope in an hour we'll meet and discuss our new results in Vladivostok. Thank you.
Раз. По-моему, он не работает. Горит? Все, работал. Excuse me. Well, dear colleague, I am glad to see you in our session, the nonlinear and Teragertz photonics. And we have several very interesting reports. And first our reports from Alexei Balakin from Lomonosov Moscow State University, Physical Department. Nano and micro-size targets for generation of Teragertz waves. And please.
Yes. Thank you, Chairman, for announcement of my presentation. Okay, this work has been done in cooperation between our group from Moscow State University and from Institute on Laser and Information Technologies in Shatura, Moscow region. Okay, first of all, motivations. Everybody knows that there is a high demand for stable, intense terahertz radiation sources which could be applied for nonlinear terahertz photonics and for investigation of extreme properties of matter. And taking into account that today we have wide enough availability of sources of femtosecond laser pulses, these quite high energies, up to few millijoules per pulse. And these laser sources could be applied as excitation source for elaboration of efficient nonlinear emitters for generation of very wide spectral radiation in a very wide spectral range from X-ray up to terahertz range. Okay, and so we are searching for new approaches and schemes for elaboration of multispectral radiation sources. Okay. Next slide. Here, I would like just remind you a few points about commonly used emitters, terahertz emitters, which are based on excitation with optical radiation. And these emitters for conversion of optical pulses into the terahertz ones. Okay. Here are a few methods and techniques and their advantages and disadvantages. First of all, the more useful and more easier to use and more suitable emitters are based on solid-state optoelectronics, and they provide high efficiency of optical to terahertz conversion, but there are few disadvantages such as saturation and optical breakdown if we like to get larger terahertz emission power. And terahertz spectrum, generated terahertz spectrum is limited by few limits, not only by optical pulse duration, but also is limited by the solid state emitters itself. Okay, and so we look at the direction of laser-produced plasma emitters. And here I also listed at least three sources. First, solid-state plasma. Next, laser-brittle plasma in gases and in liquids. Okay, I won't read green and red lines here, but everybody knows that of course, the highest possible efficiency of optical Teragertz conversion is produced by solid state laser plasma, but there are few disadvantages which are limited pulse periodic source. And if we speak about gas plasma, we have, of course, we have low efficiency of optical Teragertz conversion. And if we come to liquids, okay, we get a higher efficiency of conversion, but it's still low if compared with solids. Of course, these two media are not real competitors to solid-state plasma. But nevertheless, here we would like present our results in increasing of efficiency if we go from gases to clusterized gases target. It's first part of my presentation, and so named nano-sized targets, and here we will use a liquid metal media, and exactly liquid metal droplets, and also liquid micro droplets which are produced from dielectric media. Okay, so first part. Just remind how to get clusters. It's a few words about gas cluster generator. We use very well-known adiabatic expansion method of gas into vacuum. Okay, there is a gas under high pressure, and it passes through conical nozzle, special form of nozzle, into vacuum, and due to adiabatic cooling, we can produce few tens nanometers in diameter balls, so named clusters. This object, I told that it has diameters up to tens nanometers, and could include up to million atoms or molecules of original gas, which is here in backing pressure chamber. Okay, and usually semi-classical approach provided by Hagena is used to estimate size of clusters which are produced by adiabatic expansion method. But we did true numerical calculation estimations of clusterization process, and here some results of distribution of argon density, and we found out that there is quite interesting behavior of jet, of gas cluster jet, because in any case we get not pure clusters, we get mixing between not clusterized molecules or atoms of gas and clusterized, and it's proportional. It's around, okay, we could clusterize in the better case up to 40% for all percent of total gas. Okay, and here there is few cross sections just crossed in perpendicular direction of jet axis, and you see that there is very interesting distribution of average cluster size, and also average cluster concentration has also so interesting behavior. So we supposed that this gas cluster jet is quite unique object. We may change laser cluster interaction process by changing focus position along the jet axis. Okay, and so here just experimental setup which was created. We created one setup in Moscow State University, and this particular vacuum camera is in Shatura in IPLIT, Institute of in our academician institute. Okay, and here we provided possibility to move in three directions of our jet, and to investigate as vertical direction along jet axis, as well in perpendicular direction, and here it's XY direction. Okay, and here results which are taken from argon gas cluster jet, and we measured angular pattern of Teragertz emission for two positions of our focusing point. Just below nozzle output edge, it's around 1.5 millimeter far, and here you see average concentration and average size of clusters in this cross section. It's quite homogeneous, and second cross section here you see, and there are large clusters in periphery parts of the jet, while and in the axis of jet there are still low size clusters. And you see that there is a great difference between as terahertz power generation. Okay, it increased more than 10 times if we go from here to here, and also pattern or angular diagram is also becomes twice narrow if we go far away from nozzle output edge. But here I would like to present you our recent results, which are devoted to our quite a new project, which is connected with generation of charged particles from such media, I mean gas cluster jet. And here you see XY map for terahertz emission. Okay, red is maximum and blue is the minimum signal value. And electrons emission map, which is measured simultaneously at the same time when we measured terahertz emission. And here you see, and here you see also CCD image of electron beam profile, which is secondary emission from a scintillator. And as you see, we have quite directed beam, electron beam, and it's the angle is about 100 milliradian. And we estimate average energy of generated electrons. It was around 100 kiloelectron volt. But unfortunately, charge of electron bench, of single electron bench, was estimated at the level of few tenths of femtocoulomb. But nevertheless, our colleagues from Moscow Engineering Physical Institute could take this beam and preamplified it in 7-section preamplifier up to 8 MeV, and with next amplification up to few tenths of MeV, and such short electron benches could be used as seed for next for say free electron laser, and these results have been updated in the frame of our so-named synchrotron project. It's quite interesting because these signals, I mean terahertz and electron emission, has different, not only different dimensions, special characteristics. I mean optimal values of the signals. They have different optimal parameters from point of view of temporal, from point of view pulse wide. In our previous papers, we show that optimal pulse length for Teragertz emission is around 200 femtoseconds, and we get something like 2 maxima dependence. This minimum value for short pulses. But in contrast, electron emission demonstrates one peak dependence from femtosecond pulse duration. And the maximum electron signal corresponds to spectral limited optical pulse. In our case, it was around 40 femtoseconds. But nevertheless, it's very interesting. And both signals increase when we go down along cluster jet axis, and it becomes maximum at near at this position. It's here 13.5 and 13.5 and to up to 15 millimeters. Okay, and here I stop this micro or this nano-sized target, and I'd like to come to micro droplet part of my presentation. And here you see micro droplet generator. We took this guy from another our project, which we realized together with colleagues from Institute of Spectroscopy from Troitsk. And this source was elaborated for so-named extremely ultraviolet lithography, XUV. Oh, sorry, I will try to be shorter. And okay, for this case, they applied so exotic eutectic alloy, which contains tin and indium substances. And here tin is used for emitting of 13.5 nanometers XUV radiation, and indium helps to decrease melting temperature and also to increase aggressive properties of tin, because pure tin is quite aggressive substance. Okay, and here you see that we needed to heat and to get stabilized heating here, and also problem this vacuum camera, which this camera which get these micro droplets because of oxidation. We need to go down up to at least 10 minus 5, 10 minus 6 millibar pressures. But nearly the same generator we elaborated for dielectric substances such as distillate water and isopropanol, for example. And these dielectric substances are not needed to be heated, and it's more less complicated setup. Okay, here experimental scheme. Okay, here we provided two pulses irradiation regime, and also could provide angular measurements. And here you see two experimental setups. This one in Moscow State University, and this one in our Shatura Institute. Okay, and here you see quite complicated thermostabilization and melting part, and here is quite easier part for preparation dielectric microdroplets. Okay, here just a few points about our micro targets. We used average size around 50 microns. Okay, here you see repetition rates, and here you see how laser beam diameter corresponds to droplet diameter. It's around 3 times less. And for control of interaction, for control of droplet size and interaction process, we used shadow photography technique. And here you see resolution in time and in space, in spatial resolution of this method. And here few results which, okay, this one and this one, you see that for efficient generation of Teragertz radiation, we must apply double pulse excitation scheme. You see here 2 order of magnitude increasing. Sorry. And also not only time delay, but also energy ratio between pre-pulse and main pulse, which excites our droplet. Okay, here just a few slides about spectra of X-ray and Teragertz signals. Here about radiation patterns for 2 different sizes of microdroplets. And here this slide and this slide are devoted to our results, which we obtained in experiments these dielectric microdroplets, and in particular when we used distillate water as a source for such microdroplets. And here just remark that for isopropanol, X-ray power was the same, but Teragertz power was 1 order. Okay, so I'm just finishing, and here conclusion. So we demonstrate theoretically in numerical calculation and experimentally possibility to use gas cluster jet as a good and new scheme for efficient generation, Teragertz generation, and for managing of its direction, and also observed joint generation of Teragertz and electron beams in such media, I mean gas cluster supersonic jet. And this part is devoted to our results, which was obtained with micro size micro droplets, metallic and dielectric as well. So thank you for attention, and I'm sorry for use more time than it was.
Thank you for interesting presentation, and please questions for Alexei, and short questions, one or two. We have not so many time. Please. Yes, please.
Thank you very much for the very nice presentation. Could you please explain me why your, how to say, diagram of radiation, of Teragertz radiation, are so unusual? Yes. Like, no, a little bit. Yes, like this one. Why this diagram is so, how to say, raised? I know.
Thank you for the question. Okay, here we believe we estimated why it could be, and we estimated that we observe interference of two contributions from dipole and quadrupole currents, and one more point, that this source is just near to opaque droplet, which is not transparent for Teragertz radiation in normal. And so we observed, besides interference of these two contributions, we also observed diffraction, which occurs near this. Yes. Okay, and here just such strange behavior could be associated with interference of these contributions and falling diffraction, because it's and unfortunately we couldn't write it, calculate it analytically. It's necessary do numerical simulations.
But I think it can be done for the, how to say, for radio frequency.
Maybe later you can continue discussion. Unfortunately, we haven't time. Maybe somewhere have some another question, but after presentation. Let's thank you very much. And our next report, nonlinear Teragertz optics, and our from ITMO University. Maxim Melnik, yes. Please here. Can begin.
Does it work? Huh? Раз. Ага, все. А можно молчок? Okay, thank you. So my name is Maxim Melnik, and I'm glad to present you from the behalf of my co-authors the talk Nonlinear Teragertz Optics, where I cover our recent results in this area. First of all, I want to thank Programming Committee for the possibility, for the invitation and possibility to give a talk on this conference. So our work was conducted in the laboratory from the Second Optics and Femtode Technologies of ITMO University, where we, for the last 15 years, works in the field of generation from second radiation, studies interaction with different materials, pump probe spectroscopy, as well as Teragertz generation. And when we speak about Teragertz generation in general, our laboratory have two main topics where we work in Teragertz region is Teragertz radiation generation in liquids, and study the Teragertz nonlinearities, as can be seen on this on this slide. Recently, we were the authors of the book called Teragertz Liquid Photonics by Professor Xichen Zhang, and we have two chapters in this book, one related to the Teragertz wave generation in liquids, another one for giant nonlinearity of liquids in Teragertz frequency range, and I will cover the second chapter in this talk. So to begin with, I want to say that there is a lot of different Teragertz applications, and almost all of them can benefit from the increasing of the energy and intensity of Teragertz sources which can be used in these applications. And this ability to have these sources with larger intensity, larger energy, bring us to the idea of possibility to observe the nonlinearities in this frequency range, which was not possible like 15 years ago, for example. And here you can see the example from one of the overview over the topic of laser-driven strong Teragertz sources. And among them, the most widely used is the generation of Teragertz from plasma, from optical rectification in crystals, and also plasma can be different from gases, from solids, and as well from liquids. And one of the most widespread method for Teragertz generation, especially intense Teragertz generation, is the optical rectification in organic and non-organic crystal, which is presented on the right side of the screen. So lithium niobate is one of the most useful crystals for this topic, and can obtain the energy of 125 microjoules, so which is enough to observe the nonlinear processes in the material. So the beginning of our interest in the nonlinear Teragertz optics topic was started with a paper in 2015 written by Professor Kozlov in collaboration with Professor Boyd, which is studied the theoretical approach and demonstration that the nonlinear effects of the material in Teragertz frequency range caused by the vibrational mechanism. And they use the classical model of anharmonic oscillator to obtain the formula that you can see on the screen for N2 estimation of the material. This formula is useful since if you see the parts of the formula, all the parameters that included there are characteristic parameters of the medium, and you can see them in any book and use it to estimate the nonlinear refractive index of this material in Teragertz frequency range. Later, we use the same formula in order to calculate the nonlinear refractive index of different solids. We start with solids. You can see here the result for example, zinc telluride, zinc selenide, and lithium niobate crystal. For example, lithium niobate has the nonlinear refractive index of 6 times to the 10 to the minus 11 watt per centimeter square per watt, which is 4 orders larger than in visible and infrared range. Also, in this work, we cover we analyze the possible parameters that can directly inflict in the increasing of N2 of the material, which is set on the right side of the screen. And after the analysis, we understand that all these parameters are met if we switch from the solid states to the liquid state of the material. And it's important to say that despite the fact that the liquids are isotropic materials, if we go to the microscopic scale, all molecules have this induced birefringence, and it eliminated to zero only after the averaging of all molecules. However, the theoretical model that I presented earlier actually introduces this presence of this birefringence, which can help to better understand the effect under the Teragertz radiation light of the material in this frequency range. So we also need to change some parameters that include in the formula of N2 estimation, since we switch from the solid state to liquid state. For example, we switch the dimension of unit cell to the size of the one molecule, for example. And our first model that we use the formula was the simple water molecule, and for water we obtained the N2 value of 7 times to the 10 to the minus 10 centimeters square per watt, which is 1 million times higher than in infrared and visible frequency ranges. And this is our theoretical results, and we want to prove them experimentally. But before this, we need to understand the possible experimental approaches that can be used in terahertz frequency range. Historically, there is a number of different methods that can be used to estimate N2 value of the material. Two most famous of them is pump probe spectroscopy and Z-scan technique. So we use the second one, but before to use it, we need to estimate what parameters of the system should be considered in order to obtain correct results. Since this Z-scan technique, as can be seen here, was proposed in 1990s for strictly monochromatic radiation, but for the last 30 years, these methods showed its usefulness even for femtosecond pulses with pretty broad spectrum. So just brief information, the Z-scan technique is the main idea is present in this animation. So when we put the medium under investigation at the focus of the spherical beam, convergent spherical beam, this medium starts to behave as the second thin lens, which changes the distribution of the light in the far field. And in this far field, we put the aperture and look at the changing on the the energy that passed through this aperture or pinhole, and obtain the characteristic curve of that scan, which can be presented on the bottom of the screen. So it's a peak to valley, and from this peak to valley ratio, and knowing the parameters of the system, we can estimate N2 value. We conducted the analytical numerical simulations of this Z-scan technique in case of terahertz generation. As a medium, we used zinc selenide sample with different thicknesses, with different wavelengths in terahertz frequency range, as well as different durations of the pulse itself. So as you see at the bottom of the graph with the green curve, we have our simulation results for the pulse duration of 10 periods, and its comparison with the analytical expression from the conventional Z-scan technique. We see that there is a very small discrepancy, around a couple of %. However, if we switch to the few cycle pulses, as the upper picture shows with yellow, and when I say a few cycle pulse, I mean extreme case of one single cycle pulse. It presented on the left side of the screen and its spectrum as well. We have very large discrepancy between an analytical curve and the simulation curve. And in order to investigate when we have these two completely different results, and we need to understand what we need to set our system, how we need to set our system in order to obtain the green result, not the yellow one. So we introduce the new parameter, which call L-bel delta Z to the right side of the screen, which is just the ratio between size of the sample and the special size of the terahertz pulse. And you can see the smaller this value is, the smaller the error of the difference between analytical expression graph and the simulation graph. So since we cannot make the thickness of the material 0, so we need to keep the idea that this value L-bel delta Z should be smaller or equal to 1 in order to be sure that they're going to be the smallest mistake possible in the N2 estimation. So now I switch to the experimental scheme of our Z-scan measurement. We started to do it with water first, and then with other liquids. Here you can see the experimental setup. We have the femtosecond laser system that pump the lithium niobate crystal in order to produce our terahertz radiation, and then using parabolic mirror, we focused the light, the terahertz pulses onto the water jet. We use jet in order to eliminate any thermic nonlinearity, because we set the speed of the jet so each new pulse of terahertz radiation with the frequency repetition rate of 1 kilohertz interfere with new set of water, and this is how we eliminate the summation of thermal effect. Our jet was produced with a compressed tube and 2 razor blades and the shape of a pellet, as can be seen on the screen here. And the jet was had thickness of 100 micrometers, and according to our previous theoretical investigations, so value of L by delta Z for this system is 1/3, so it's smaller than 1, so we fulfill these requirements in order for this case. And here you can see the results of our experimental comparison with theoretical curves for 4 different liquids, for water, ethanol, alpha-pinene, and 2-propanol. And to the right of the screen, you can see the calculated values from these curves. So all 4 liquids show the very much larger N2 value than in infrared and visible range. For easy to understand, here's a table where we can compare the N2 values for these liquids in visible and near infrared, the data from the experiment, and data from the calculated values. Also, you can see that the experiment and calculated values have a pretty similar to each other. And then I want to switch to the idea that there's a lot of different groups that work in the same field to study the nonlinear effects in the liquids. And not all of these groups used our proposed vibrational mechanism of nonlinearity idea, which is again set here. And for example, one of our colleagues from Germany stated that this idea is the idea of this vibrational mechanism are not correct, since they conduct measurement of nonlinear absorption in the Teragertz frequency range for different temperatures. And since our formula consists the thermal expansion coefficient to the left side, it's alpha, yeah, alpha tau. Then for water, this coefficient is set to 0 for 4 degrees Celsius. So they said that for 4 degrees Celsius, our nonlinearity should be 0 as well. But they measure the nonlinear absorption and show that there is no difference between nonlinear absorption at 4 degrees Celsius and 21 degrees Celsius, and stated that maybe the vibrational nonlinearity theory are wrong. Then we decided to elaborate on this and understand what is the nuances, so they obtain these interesting results. And we came to the conclusion that there is no reason to estimate the nonlinear response of the refractive index in Teragertz frequency range based on nonlinear absorption, because direct contribution to the nonlinear refractive index in Teragertz frequency range comes from the resonant interactions and oscillations in the infrared range, not in Teragertz 1. So their work's not correct, and in order to prove it, we conducted more series of experiments to show the temperature dependence of N2 for water. Here you can see the setup is pretty similar to the previous one. One addition is that we are at the temperature control unit, and the detector of the temperature, we located it nearby the jet itself in order to measure the temperature of the jet that interact with laser light directly. Here you can see the electric field and spectrum of our Teragertz system in the far field. So we obtain the Z-scan curves, conduct the scan measurement for temperatures presented on the screen. Unfortunately, we can change the temperature from 21 to 14 only because our temperature control unit was an open type, and we cannot go below this temperature because it starts to there's the introduction of the presence of people and all these things to the results. So we can change only from 21 to 14 degrees. However, you can see that if we increase the temperature, we increase the peak-to-valley ratio for the curves, and using the formula of N2 estimation from this, where peak-to-valley ratio is delta T here, we calculated the N2 values for the different temperatures, and it can be seen directly that it's increasing with the increasing of temperature. So there is direct dependence of N2 on temperature as we presented earlier. And in order to compare this with our experimental analytical equation that was used in previous works, we introduced the temperature dependence in alpha coefficient, and then compare the results of analytical expression with our experiment. We conducted a series of experiments. It's only 3 here. We do it because we need to show that there's a repeatability of experiment. You can see that there is a very good agreement between experiment results and theoretical results, and theoretical curve go to the 0 around 4 degrees, just as we as we expected. And then this is can be seen as approval that there is a nonlinear refractive index dependence of on temperature, and then our vibrational mechanism of nonlinearity makes sense in terahertz frequency range. And at the end of my talk, I want to cover another interesting observation that we have in our laboratory group. It's an observation of quadruple frequency generation instead of triple one. Here you can see the setup and the pictures from the experiment. So when in lithium niobate crystal we generate the terahertz radiation, it generates in a very thin layer of the crystal, and then terahertz wave propagate inside this lithium niobate crystal and have influence of third order nonlinearity and should produce the third harmonic. However, after we conduct this experiment, we obtain the following results, where we can see that at the third, tripled frequency from the maximal frequency, from the central frequency of the pulse, we have pronounced dip, while there is a non-zero energy generated in the region of quadruple frequency, which is not usual for infrared or visible light. And we investigated this further with the theoretical models, and which is result presented here. We can see that this shift from the triple to quadruple frequency generation occurs only for the electric field with the very few oscillations, not very few, but exactly one oscillation. And when we switch to the 3 oscillation of the pulse, our theory showed that the frequency generated is a tripled frequency generation as expected. And we connected it with the 2 things. One thing is that as you can see from the left side of on the left picture, the spectrum of single cycle pulse are a non-symmetrical one and pretty broad, and because of this, the 2 effects, nonlinear third order nonlinear effects, namely tripled frequency generation and cell phase modulation, start to interfere with each other in spectrum region, and you can see that they have different sign, and at the exact position of tripled frequency they cancel each other. So this is our possible explanation of the obtained results. And this is it for my talk. Thank you for your attention, and I'm glad to answer the questions.
Thank you very much. Very interesting presentation. And questions? Yes, please.
Thank you very much. It was a very interesting presentation. Maybe I don't understand you well, but how you avoid saturation of absorption in the terahertz range for water?
Because we use very thin sample. We have 100 micrometers thickness of the jet, and we eliminate the nonlinear absorption by using the Z-scan technique.
No. I mean linear absorption, simple absorption.
Yeah, I understand. We have very thin sample.
How it will be seen? How
100 micrometers is enough.
100 micrometers is thick, I think.
It's enough to
because you see the absorption coefficients at that spectral range about 10 and 4 how to say?
Yeah, it's pretty large. I understand you, but with this thickness of medium, we able to gather the signal after the jet, and we work with this signal. Yeah, it was much weaker than if we use non-absorptive material. However, we can say that that linear absorption does not interfere with our measurement, because if we go for these pictures, you can see the results for, секундочку. For alpha-pinene, and alpha-pinene is a non-polar liquid, and it does not absorb Teragertz radiation at all, and we have the same result as for absorptive materials. So
looks strange because when I see such kind Z-scan picture, I believe that the distortion of this Z-scan picture are associated with absorption. This is a typical. You, as far as I remember, you are using the simulation from the head side.
I want to say
yes, and there are opportunity to put absorptions in this simulation, and we see the same picture.
I agree with you that this noise that we have on the experimental result is based on the thing that we have very large absorption and our signal is pretty weak, but we still have a signal, and
maybe okay. Thank you.
Thank you.
Thank you very much.
Yes, please.
My question is about your scheme for Terahertz generation lithium niobate. Is it a simple non-phase matched generation? Do you use Cherenkov angle or tilting pulse front?
It's phase matched. I can show you here on this.
Why it is phase matched in collinear direction?
You can see here on the figure, on the picture, that our crystal is not like the. So there is a cut in a right angle, so we have.
So it is a scheme only. Yes, I see to the left.
For the scheme, yeah, it's just for simplicity.
Yes, and I saw this picture in other cases also, and was wondered.
Please.
Thank you for your presentation. Could you tell me, please, is there any possible ways to prove your theory about temperature dependence on a nonlinear coefficient?
Yeah, I think that I understand that the changes from 14 to 21 degrees is not enough, and we're working on the possibility to do it like around 4 degrees and even below 4 degrees before the crystallization of water, because in our idea after below 4 degrees we should obtain the opposite sign of N2, and then this will prove our theory even more than we have right now.
Thank you.
Thank you.
Okay, thank you. Thank you very much for your talk. And my question is about you say that you control the temperature incorporating in your measurement of N2, yes?
Yes.
But how do you control this? You show nothing about you just vary the frequency and measure the N2, and for such certain frequency your N2 does not change, and so this is the effect that you give you this that for 1 kilohertz you have no effects of your temperature incorporating in your N2 measurements. How do you control this?
How do we control that our laser does not hit the
yes. Yes.
We control it by, as you said, by the combining the repetition rate of the laser and the speed of jet. We have calculation. I don't present it here of the thermal N2 values, and for this repetition rate, the thermal nonlinearity is order of -17, while we have -10 here, so it's like 7 orders smaller, so we say that it's instantaneous effect regarding to the thermal nonlinearity.
Okay, and you see when you just decrease the flow rate of your water, your N2 becomes higher, yes? You see it in your measurements.
We should see this, yes, if we decrease the flow rate.
You should see, or you see?
I'm not the experimentator, so
okay.
I'm not able to answer this question.
Okay, thank you.
Well, maybe after session you may speak about it more precisely. Well, if we haven't any question,
thank you.
Thank you very much. Another time, second time. Yes, and our third on the opportunity of Teragertz radiation detection using fluoride nanoparticles. Please. And from Zavolsky.
Okay, thank you very much, dear colleagues, dear chairman, dear colleagues, ladies and gentlemen. Thank you very much for the opportunity to present our modest presentation on this conference. As you see, I will talking about opportunity of terahertz radiation detection using by nanoparticles.
Maybe you could speak from this table because camera off.
Ah, yes, okay. I'll try, but it's not convenient a bit. No. Okay, yes, I can see. Okay, thank you very much again. Oh yeah, so I will talking about idea how to visualize terahertz radiation using nanoparticles. As you can see, I present two organizations. One of this is a Kazan Physical and Technical Institute named by Professor Academic Zavolsky of Kazan Scientific Center. And the second organization is the Kazan Federal University. I think you understand why I, present the presentation from the two organizations. Yeah. Okay, I will take about the main ideas. And my goal of this presentation to present the idea, discuss it, and maybe excite interest in this field and involve somebody in the collaboration in this field. I will talk about approaches, about background, of course. Then I will use some basic estimation, very simple estimation. Then I will talking about nanosensors, which are the main subject of this presentation, about principles of measured temperature using using by nanosensors. And this is a question a little bit connected with the previous report, because as we believe, terahertz radiation a little bit heated even nanoparticles, even nanoparticles of water. So this is the reason why I'm talking about a little bit more. Yes, I will talk about how to prepare these nanoparticles, about a little bit experimental data, and then I will make some estimations and allow myself to do some conclusion. Okay. First of all, I would like to attract your attention to the studies of, it's not operate? Laser is not operate, yeah? Okay, so to this publication where was presented the ideas how to visualize terahertz radiation using metallic nanoparticles, using the principle of terahertz radiation conversion into the heat, and then observation of the heat field of the nanoparticles, metallic nanoparticle screen by thermovision system. Our idea is to refuse this thermovision system at all, and using nanoparticles which can emit fluorescence, and using the thermosensitive fluorescence visualize terahertz radiation, measure and visualize terahertz radiation. This is it was previously very well shown by Professor Moldasanov and his colleagues. Yes, and I will talk a little bit about this a little bit later, but I would like to pay your attention to the basic motivation why nanoparticles can be used for any type of visualizations. Nanoparticles, if we will decrease the radius of materials from millimeter scale to nanometer scale, we will, of course, decrease the mass of this particle. And also, we can decrease specific heat of the material. So it is very easy to heat nanoparticles by very low external radiation. Doesn't matter which kind of radiation. It can be, for example, terahertz or usual light. If we put these nanoparticles into low thermal conductivity matrix, and this nanoparticle will be isolated, so we can achieve very high spatial resolution of nanoparticles with a high sensitivity. So this is a motivation why we are proposed to use nanoparticles for the visualization of Teragertz radiation. Yes, as I told, Professor Moldosanov considers the metallic nanoparticles. In his paper, he considered some type of metals, but the most interesting result was achieved on nickel nanoparticles, which place it in the gelatin. These nanoparticles has the radius R0, for example, with specific heat about CNP and thermoconductivity lambda MP. The same parameter we can introduce for the matrix, but these parameters are marked by index M. Okay, the temperature behavior of nanoparticles will be described by thermoconductive equations with the heat. Oh, sorry, it's necessary to show how to do it. I don't know. Well, the heat sources matrix QR. In fact, this QR is how to say the heat density. Volume heat density. So if we will try to solve these equations in a steady state condition, we can get the, how to say, the solution of this. Okay, okay, thank you very much. So the solution of this equation are shown here. But if we will use this formula to calculate how much temperature will change when we try to heat the nanoparticles by Teragertz radiation, we need to know some basic parameters of nanoparticles. For example, for several nanoparticles, data are presented on this slide. I put additionally to this table aurum nanoparticles, nanoparticle of water, and some fluoride nanoparticles. We consider the situation single core nanoparticles, which consist of, for example, only with nickel or aurum or maybe water. And consider the situation such name core shell nanoparticles, which, for example, core must be metallic nanoparticles or water cluster or something like that. Doesn't matter which kind nanoparticles, but we have to use shell from the fluorescence materials. For example, it will be fluoride nanoparticles doped by radioscience. Okay. If we will try to, following by Professor Moldosanov calculation, estimate how temperature of nanoparticles will change with absorbed radiation, Teragertz radiation, we will get similar papers. So nickel, as you see, has a very good properties. And it's easy to heat these nanoparticles by Teragertz radiation. But in fact, these nanoparticles have not any fluorescence properties, so it's not possible to use fluorescence sensitive properties to measure temperature of these nanoparticles. So we have to go to core shell, as I told on the previous slide. Yes, but you see, in first case, the minimal detected terahertz power will be only few nanowatts. But the second, we lost a little bit sensitivity to compare with the previous one, and it will be the difference temperature which less than, for example, for the first graph. But if we consider thermovision system with the best properties, we can achieve minimal variation of temperature less than 12 milli-K. But unfortunately, in that formula, Professor Moldosanov did not take into account the absorbance of nanoparticles, absorbance capability of nanoparticles about Teragertz radiation. And we have to put additional parameter named A, it's marked by red, which, reflect absorbance probability, absorption coefficients of Teragertz radiation. For example, I put some data about not absorption coefficients, about absorbance of nanoparticles, which can be calculated from the Booger law. And we get estimation of parameter A between 10⁻² up to 10⁻⁵. It's too small, unfortunately. Too small, unfortunately. But it means that the detectability of Teragertz radiation will be low for the most of used materials. But if we consider the material in the real Teragertz range from at about with a frequency about 6 terahertz or something like that, we will see the absorption coefficients can be drastically improved because in this spectral range the absorption coefficients achieve 10 to 3 or 10 to 4 centimeters, inversal centimeters. So in this spectral range, the absorbance coefficient A can be good, and we will see something. We will try to eliminate the now nanoparticles by Teragertz radiation. So we will see the changing of the temperature. As we make this similar calculation, and our estimations are shown on these graphs. So if we will consider, for example, nanoparticles with a core from water, we will get, for example, detectability of Teragertz radiation on the level about tens of microwatts. But we don't know anything. I think we will understand how much it is. We need to know what the minimal variation temperature we can detect using the fluorescence technique. So I need to tell you about the fluorescence temperature nanocenter principles. In fact, there are 6 parameters. It can be any spectroscopic parameters which can be temperature sensitive. So usually we are study the changing of the fluorescence spectra, marked like a band shape with the temperature, but it can be, we can use the spectral shift of spectra of fluorescence with the temperature, or changing of intensity, or the lifetime of fluorescence, or bandwidth, and so on and so on. In order to realize this thermosensor, we need to put our terahertz sensitive, which the agent which will be absorb the Teragertz radiation somewhere inside of matrix, for example, from gelatin, and eliminate of this agent, these nanoparticles by the laser, in order to stimulate the fluorescence. If we will eliminate this system by Teragertz radiation or any kind of radiation, doesn't matter which one, we will change the temperature of nanoparticles, and it will be reflected in their fluorescence. So this is the main idea. Yeah. For example, we can consider very simple model, consists of 3 levels, one of ground state and 2 excited state levels, which separated by energy gap about let it be 100 of universal centimeters. If we will excite this system by radiation, we will see the fluorescence from upper or lower levels to the ground state, and this fluorescence will coincide with the wavelengths lambda 1 or lambda 2. If we will measure the fluorescence intensity on these wavelengths, we can measure the temperature of these nanoparticles. But, the main parameter of this fluorescence thermometer are the luminescence intensity ratio, marked LIR, which is dependent on the temperature, and this is a ratio of appropriated intensity at lambda 1 and lambda 2. Of course, if we consider the situation of levels which are separated by energy gap delta E, it will be mean that we can use Boltzmann law in order to estimate how the fluorescence intensity will be changed with the temperature. There are 2 main parameters for the fluorescence nanosensor. This is absolute SA and relative SR thermal sensitivity, which we can use for our fuse estimations. Concerning us, we need how small variation of temperature we can measure using this technique. It can be expressed like here. If we will consider the situation when we can measure fluorescence intensity with a high accuracy, for example, at about, it's mean signal noise ratio, say. It's, for example, if we will consider the signal noise ratio about 0.0%, this is a good for the real measurements. So it means that we can measure the difference of temperature of nanoparticles with accuracy about few milli-K. So it's good result. It's much more better to compare with the thermovision system. So I think this idea is, how to say, readable. Okay, a few words how to create nanoparticles. We have a lot of experience to design different kind of nanoparticles. For example, praseodymium doped lanthanum fluoride nanoparticles are more temperature sensitive. It can be produced from the water solution by cooperative technique. And depending on the peculiarity of our synthesis, we can produce any kind of nanoparticles with a different shape, different morphology, with a different sizes, and additional treatment of these nanoparticles, we can increase their sizes up to submicron sizes. This is a photos of, no, not photos, reality. It's TEM imaging of these nanoparticles, transverse electronic microscope. And you can see we can produce nanoparticles with different sizes and with different morphology. For example, on the left photos, you can see the nanoparticles of nanodiscs. On here you can see the nanoparticles with a spherical shape. Yes, because we are producing the nanoparticles from the water solution, we can easily create nanoclusters of water inside of nanoparticles. So we can automatically produce core shell structure with the core formed from the water. Yes, and few words about the fluorescence properties of praseodymium ions, which are needs to use fluorescence thermal sensitive fluorescence principles. Yes, there are a lot of transition from the excited levels of this ion. Concerning us, we are interested in the transition from the 3p1 or 3p0 level to the ground state of praseodymium ions. You can see on this graph, you can see the difference of fluorescence spectra with the temperature. And if we will take this data and put this data in our formula, we can estimate, accuracy, which, okay, I will finish. Okay, so we can realize very high signal noise ratio. We can use not only this kind of nanoparticles, in fact, there are a lot of kind of nanoparticles with a different kind of sensitivities. And our estimation shows that the minimal detectable temperature, changing of temperature will be about 6 mK at 100 K of ambient temperature for nanoparticles. But we don't know about minimum detectable terahertz power. We will do, at the beginning, we have to measure the absorption coefficients in terahertz for the nanoparticles. Unfortunately, the absorption coefficients at the wavelengths, as a frequency of terahertz which are using in our experiment was very small. It's only about 1 centimeter. It's nothing, because nanoparticles almost completely is not absorbed terahertz radiation completely for this frequency. So, but if we would change, for example, the frequency up to 6 terahertz, the absorption coefficients start to be very, very high to compare with 0.6 for 600 gigahertz. And our estimation for the detectable terahertz power is few microwatts. We tried to measure direct experiments. It was done few weeks ago, but unfortunately we did not observe the real good signal. We will see something, but we believe that if we will continue these studies, we can get some interesting result. Yes, this is about our dream concerning how to realize system to visualize terahertz radiation. And in order to realize it, in fact, we need to increase the absorption coefficients to radiation by nanoparticles. This is the first problem. And the second one, we have to find out very good fluorescence sensors which can demonstrate high temperature sensitivity. Thank you very much.
Thank you very much for good presentations and questions. Yes.
Comparing your possible detectors with other bolometric type terahertz detectors, I think it will not have the record speed or record sensitivity, noise equivalent power, and so on. But what do you say about the spatial resolution? Yes.
Yes. I think it can be better, but I'm not sure, because this is let me tell you, we are we are too young in this subject. You see, me, not you, me. I start to try to measure something in terahertz only a few months ago. So this only idea. And this is why I try to explain the idea. Maybe you can find the opportunity how to use this kind of opportunity to measure something in terahertz radiation, in terahertz spectral length.
I think spatial resolution will be your most point.
Yes, I think it will be better, because you see the sizes of particles are nanometers scale. So yes, and another opportunity. Let me show. Another opportunity. We can realize, maybe we can realize something like a usual visualizer for the infrared radiation. Why not?
Thank you for your presentation. Could you tell me, please, is there any possible ways to use your cell and changing their properties by external forces, and maybe create something like special late modulator?
Oh, it probably yes. I'm not sure, because you see, in fact, there is a different kind of fluorescent thermometer. Maybe the nanoparticles is not, how to say, best. We are thinking about using, for example, the combination, for example, nanotubes from carbon with how to say, with fluorescence dyes. Maybe this is a way, or maybe using the metallic nanoparticles, or again, carbon nanotubes with quantum dots. So I think maybe it will be, how to say, maybe it will be interesting to use.
Okay, thank you.
Thank you very much.
Thank you for questions. And please, maybe some has another question. And I have, yes, I have a question about your experimental scheme. You embedded the nanoparticles to gelatin, and gelatin has relatively high Teragertz absorption. It's maybe can you? What do you think about it? It's
yes.
Problem or no?
Yeah, I understand. Thank you very much.
And
yes,
another...
Yes, I know this one, but unfortunately, first of all, we have not good terahertz sources. We have the terahertz which can...
backward later, yes.
Which unfortunately is not operated good. So the maximum frequency which we have in our lab is only 600 gigahertz. Yes, for this spectral range, gelatin is okay. But of course, we will try to go
maybe
to some terahertz. It will be not possible to use gelatin. This is the first experiments, no more.
Yes, of course, understand. Maybe, thank you. And if you haven't any question, thank you another time. And
sorry for my English.
Now our next presentations. Yes, please. Nikolaeva, yes. Please, this one. And our next presentation from Lomonosov, Moscow State Technical University. Teragertz generation from a single chiral filament, pondomotive force versus light pressure. From Marina.
Thank you. Good afternoon, dear colleagues. Thank you that you came to hear my talk. As it was said, it is about Terahertz generation from a single color filament and about its sources of ponderomotive force and light pressure. First measurements of Terahertz radiation from single color filament in air were done in 1993 by Hamster and his colleagues. As you know, I guess, in air, direct generation of Terahertz radiation due to cubic nonlinearity is forbidden. Therefore, there was suggested another mechanisms for its generation. First one is the ponderomotive force, which comes from the gradients of intensity or Planck density in the filament. So it's directed transversely from the filament and create a quadruple local source of terahertz. The next one source is light pressure, which due to magnetic field pushes electron in the forward direction of laser propagation and creates local longitudinal dipole source of terahertz radiation. Both of these sources was used by Shkurinov and his comment to describe one-dimensional measured angular distributions of terahertz radiation in far field, and they show that Okay. And both these sources were in good agreement with the results of measurements, and it was shown that for moderate focusing conditions, these sources are indistinguishable in far zone. Also, one of these sources, namely dipole, was used in the interference integral to describe measured distributions successfully, and also quadrupole source was used to describe. Both of them were successful, and it was suggested that the full distribution will be conical with radial polarization. However, it was only one-dimensional measurements. Since then, several experiments were conducted, and scientists measured two-dimensional distributions of terahertz radiation, and as you can see, they are not conical, that is not ring. In the experiment, we saw that there are two lobes on the axis perpendicular to the laser polarization direction. In this both cases, the laser is polarized horizontally. So the purpose of our work is to characterize frequency result to the dimensional of terahertz emission from one-piece single color filament and apply plasma dynamics equation to explain this symmetry breakup in terahertz emission. For this purpose, in Physical Lebedev Institute, in group of Leonid Vladimirovich Seleznov, was created the next setup. The laser was directed by plane mirror to the spherical one and focused in some point right here. The bolometer with filters between it was placed on the horizontal board and rotated in horizontal plane, allowing us to vary horizontal angle. To vary vertical angle, we moved spherical mirror along the vertical post and adjusted position of the plane mirror that directs the laser beam to the spherical one and the spherical mirrors in such a way that for every vertical angle our focusing point is in the same position. For each vertical angle we measured the one-dimensional terahertz distribution and in such a way obtained two-dimensional distributions. Here you can see the distribution for 0.3 terahertz. In some points using wire mesh polarizer we measured polarization. As you can see for two focusing conditions, it is a ring and the polarization is radial, as was supposed in early studies. However, if we increase frequency up to, for example, 0.5 terahertz, we also see that distribution is still a ring with radial polarization. However, there is some modulations in vertical plane and our laser is polarized horizontally. But if we come to the 1 terahertz frequency, we see that there is no ring. And here appear two lobes with terahertz field which is polarized orthogonally to the laser. Laser is polarized in horizontal direction. If we increase frequency further for 3 terahertz, we see that ring distribution starts to reconstruct and radial polarization also reconstructs. Further increase in frequency of up to 5 terahertz and 10 terahertz give us full reconstruction of the ring in the far zone. To study this phenomenon, we tried to change laser polarization direction. First of all, we using half-wave plate rotated on 19 degrees, and you see that terahertz distributions also rotate in such a way that lobes stays on the perpendicular to laser polarization direction. If we use elliptically polarized laser pulses, then the ring distribution at 1 terahertz frequency reconstructs. We studied the stability of this structure at 1 terahertz by varying laser pulse energy from 0.6 millijoules up to 3 millijoules. For all energies, the distributions are qualitatively the same and have two lobes structure. To find some explanation of this, we started from plasma hydrodynamics equations and using series expansions for plasma density, electrons velocity, and of course nonlinear photocurrent, we obtain, after some math, equations for the first order nonlinear photocurrent and the second order nonlinear photocurrent. The first one is well-known transient photocurrent, which successfully is used to describe terahertz generation in, for example, two-color filaments or single-color DC-based filaments. It provides 0 terahertz signal if we use unbiased filament, and to describe terahertz emission from it, we need to use the next order photocurrent. If we come from the temporal domain to the spectral one, we can see that there are two vectorial sources. Let us call them the longitudinal source as dipole source and the transverse source as quadrupole. They would provide in the far zone such terahertz fields. Dipole source will provide us the ring with radial polarization, and the quadrupole source will provide us two lobes polarized along the laser polarization and placed on the laser polarization direction. If we want to come to the electric field terahertz, we should use interference model and second order photocurrent was placed into Stratton 2 integral, which is vectorial, and after some mathematics we obtain the electric fields of terahertz in the far zone, which consisted from dipole and quadrupole terms. If the amplitudes of these sources will be equal or quite similar, and the phase shift between them becomes around half of pi, then the destructive interference of the part of the source along the laser polarization direction would provide us two lobes on the axis perpendicular to the laser polarization, what we can see in the experiment. This is quite similar. If there would be another relation between sources, phase, or amplitudes, then we can obtain different directional diagrams in the far zone, and some of them we have seen in the experiment. So, at the conclusion, we can say that the azimuthally modulated don't-like beam with radially polarized field is the major characteristic of the terahertz emission from single color filament. When the depth of modulations reach its maximum, the two lobes in the fluence distribution appear, and the polarization of terahertz field in them is orthogonal to the laser one. The explanation of such phenomenon is found in the destructive interference of longitudinal radially polarized dipole and quadrupole radiation, with the polarization parallel to the linear laser polarization. Thank you for your attention. If you have some questions, I will be glad to answer them.
Thank you very much. Well, we have some time for one or two small questions. Please, maybe some have. Yes.
the fact I'm a specialist in Teragertz, but I would like to ask you, which kind of laser you are using to make a filament?
Oh.
Is it will be multi-mode?
No, we use. I'm sorry. We use circular symmetric mode, which we by aperture.
No. I mean laser radiation. Laser radiation. Laser radiation will be single mode, or it was multi-mode.
No, it was classical Gauss, super Gauss mode because we used the aperture. Our laser beam was passed through the circular aperture, and the mode after them was like super Gaussian.
Okay.
Single mode, since the energy is quite low.
Yeah. It's not so bad.
Thank you. Maybe another question? Only please shorter.
I saw some works of Dr. Seleznyov, and one of them showed that if you use very long filament, there is a other different pattern of this ring structure. Does your theory will work with this longer filament with a different pattern as well?
Yes, it could describe long filament as well. However, it should be some work on the way how to obtain the photocurrent in the filament.
Okay.
In the plans, we want to substitute this photocurrent into propagation equations. However, this is quite a difficult work, and we work in this direction.
Okay, thank you.
To describe other regimes.
Thank you very much for presentations. And our last report. You could show. You could leave it. Yes. And our last report from Institute of Applied Physics, Russian Academy of Science.
Irina Zotova, my colleague,
yes.
Does not have opportunity to visit the conference, so she asked me to do this.
Okay, let's start. Periodical generation of sub-Teragertz dissipative solutions based on passive mode locking in helical waveguide gyro TVTs.
Well, I will talk about the realization in the microwave frequency range, a novel type of pulse generator which based on passive mode lock effect. First of all, I would like to remind that passive mode lock is a method of periodical generation of ultra-short pulses of light. It's well known and widely used in laser physics. This method is realized by installation a saturable absorber into the laser resonator. It may be a carrier lens or something. This element absorbs low intensity signals and transmits high intensity signal practically without losses. So there are conditions in which inside the system the radiation can exist in the form high ultra-short pulses, and some small fluctuations of field are suppressed. In spectral pulses can be interpreted as dissipative solitones, formation of which is due to the balance of amplification and absorption and harmonic generation and group velocity dispersion effects. Such mechanism of pulse generation can be realized in microwave electronics on the base of two-section generator, which consists of electronic amplifier and switchable absorber in the feedback loop. The amplifier unit can be based on any mechanism of electronic wave interaction. However, because we are going to generate ultrashort pulses, this unit must provide a rather wide band. And the key element is here is a switchable absorber, which should be suitable for operating at high power in the microwave band. I must say that we don't know solid-state materials which can act as nonlinear absorber at high level in microwave band, but we know how to do this element based on electron beam electron beam radiation interaction. I will talk about it further. For the first realization ultrashort pulse generator in microwave band, we choose this scheme. As amplifier, we choose broadband helical waveguide gyro-TVT, traveling wave tube, and absorber is cyclotron based on cyclotron resonance interaction. Further, I will talk in details about these elements. Amplifier. Amplifier is gyro-TVT with helical corrugated waveguide. Helical corrugation provides coupling of two partial rotating waves of an unperturbed cylindrical waveguide. So the dispersion characteristics of the helical corrugated waveguide has a linear path that significant widens bandwidths up to 10 and 50% and reduce sensitivity to the speed spread of the electron beams. And as I said, the key element is a switchable absorber, which should be absorb low intensity signals and transmit radiations with high intensity. And it should be suitable for operation at high power in the microwave band. So we proposed the switchable absorber based on the cyclotron resonance interaction with an initially rectilinear electron beam. This picture shows as the initially rectilinear electron beam begins to rotate with absorbing the electromagnetic waves. The duration of the absorption is caused by the relativistic dependence of gyro frequency on the electron energy. The results of calculation demonstrate practically total suppressed of low intensity signal and full transparency for high intensity signal. In absorber is optimal the regime of grazing when the group velocity equals to longitudinal electron velocity. In this case, we have minimal influence between different fragments of electromagnetic pulse through the electron beam. This is an equivalent of minimal absorber inertia similar to Kerr lengths in lasers. Of course, at first we carried out the simulation and optimization parameters of the generator. In this table contains main parameters. Here you can see the results of simulation, output radiation, and radiation spectrum. I must say that pulses can be interpreted as dissipative solitons, like in optics. For more details, please see this article. Well, go to the experiment. Here you can see the 3D visualization of experimental setup, this generator. This unit is an amplifier, and this is a searchable absorber, and this is quasi-optical transmission line with which connects sections. On the slides you can see photos of main units. Here you can see the oscilloscope threshold, which detect the regime of ultrashort pulse generation due to mode locking effect. Blue curves is a signal intensity envelope, yellow curves oscilloscope trace and spectrum. This is the regime we found. In this slide you can see the experimental results in more details, so we can got generation of periodical traits of sub-nanosecond pulses, 0.4 nanosecond duration with peak power of 100 kilowatts, period rate 30 megahertz. Also, bandwidth of oscilloscope allows to detect high frequency filling of pulses. Through this, we calculate self-correlation functions, and it shows that pulses have high degree of phase correlation. Well, this is a proof of principle experiment of realization of a microwave ultrashort pulse generator based on mode locking effect. But of interest is the ultrashort pulse generation in the higher frequency ranges. I mean W band. In this band there is atmospheric transparency window, and G band. Dynamic nuclear polarization and nuclear magnetic resonance spectroscopy methods. So according to the cyclotron resonance condition, the higher the operating frequency, the stronger the constant magnetic field required. So we proposed to use helical gyroscopy to use as a searchable absorber, because it operates in the second cyclotron harmonic, which reduces the required magnetic field. Here you can see the dependence of transmission coefficient versus the guiding magnetic field. Here you can see where we have conventional regime of amplification, and where the regime of suppression incident signal. So to have searchable absorber in this element, we should work here, and this regime, this TVT, has such dependence of transmission coefficient from input power. So searchable absorption there is. Well, it's a project of W-band ultrashort pulse oscillator based on the chain of gyro TVTs, where the one works as an amplifier and the second as an absorber. It's the main parameters. I must say that each section operates at the second cyclotron harmonic, which makes it possible to reduce the required magnetic field. Here the results of simulations So according to the simulation, the peak power of generated 660 picosecond W-band pulses can be reached 400 kilowatts with Diagnostics repetition frequency. Pulses have high degree of phase correlation. And summary. Well, I can't read. Well, that's all.
Okay, thank you for presentation. And let's say things. And what about questions? Maybe you have some. I have a little question. What kind of source do you have? Maybe you repeated my source of radiation. What do you have?
Sources of radiation.
About you tell that you make the experiment for the several hundred gigahertz for the yes, it's about almost 100 gigahertz. The next.
This?
No. Next. Is this one? Yes. F almost 100 gigahertz. And what kind of source it was?
Well, that's results of calculation, of course.
It's only calculations. We
it's
haven't
modulation.
Such source. Because maybe a backward wave oscillator, it could be you can make these experiments. Okay. Another question? No? Let's thank you very much. And we have not so many time for our coffee break, but I suppose 5 or 10 minutes have a little rest. It was a last presentation in this session. Let's continue at 16:40. Немножечко, да. А вот я не знаю, парни.
Здравствуйте, а есть кто-то из организаторов на месте?
Здравствуйте.
I spent days walking the streets trying to find you. distant sound fill my head. I spent days walking the streets, trying to find you.
Здравствуйте. Вы меня сейчас должны слышать. Спокойно. Сейчас все решим. Просто у нас идет здесь и периодически другие же презентации. Не могу просто сразу всем ответить. Сейчас загрузил как раз Сергей свою презентацию. Все верно. У меня ваша... Вот это, Ольга, есть ваша презентация. Мне скинули ее только что прям девушка. Я вам выдам право ведущего, я ее сам загружу и выдам вам право ведущего. Сейчас я ее прям в данный момент загружаю. И дам вам право ведущего, ее пощелкайте, посмотрите, и потом верну Сергею право ведущего. Все? Всех вас все устраивает? В зале также вас будут слышно, я вам буду демонстрировать зал также. Ну и также слышите, вы их тоже будете. Сейчас, секунду, я загружу PDF, а то... Или это критично будет? У меня в PPTX просто не приним. Ага. А там видео, я так понимаю, какие-то, да, есть большие? А вы можете, если что, демонстрировать экран? Это я сейчас вам объясню. Просто... Смотрите, я вам сейчас выдал права. Вы внизу, где значок микрофона, камеры, там же есть значок демонстрации экрана. Вы его запускаете. Лучше, думаю, будет так, это нормально. Ну, запускайте весь экран, нормально будет. Не запускается? Сейчас, секунду. Я заберу. А вы, наверное, у вас кнопка ОК там или поделиться? Вот сейчас я еще раз вам выдам, мне просто Не переживайте сейчас. Нажимаете еще раз демонстрацию экрана. У вас есть там весь экран. Вы выбираете, также сначала нажимаете кнопочку «Весь экран». Это вкладка. Потом у вас должно, наверное, появиться, какой экран выбрать. У вас там только один, наверное, экран. Первый экран выбираете. О, аккуратно. А вам музыка мешает, наверное, еще, да? Что-то. Вот, вы выбрали. Сейчас, секунду, надо грузить только пока. Надеюсь, загрузится. Сергей, подскажите, вы видите демонстрацию экрана? Я вас не слышу, только у вас микрофон. А я, к сожалению, не вижу почему-то. А почему-то я не могу наблюдать. Да, это все окей, но... Вот я прав, потому что он пока что меня. Я пытаюсь решить проблему с... А если вы будете говорить, когда листать, это критично, я правильно понимаю? Если вы будете говорить, когда листать, если я буду листать, а вы будете просто говорить слайд далее. Я понимаю, к сожалению, просто у меня этот лиц не принимает из-за размера, он слишком большой. Сейчас я чуть придумаю. Да. Это как раз прикид, к сожалению, для этих серверов. Сейчас, секунду. Без справки вы, конечно, не можете загрузить, только когда я вам выдаю. Сколько нас весит? 33 мегабайта. К сожалению, здесь ограничение просто 30 стоит, и я просто бессилен в данной ситуации. Хорошо. А в PDF у нее там что-то исчезнет, если мы в PDF переделаем? У вас есть какие-нибудь там GIF изображения, видео изображения, что-то такое? Все, хорошо, я выполняю. Отлично. Мы можем сделать или две презентации, 30 секунд просто перелистывания, даже меньше, но зато вы покажете все. Только я просто не понимаю, как это сделать. Сейчас. Сейчас я вам права буду. Я вам буду права, у вас появился плюсик, должен быть в нижнем левом углу, верно? Вот, да, нужно нажать, там загрузить презентацию. Мой план, мне кажется, еще считается хорошим, когда мы запустим вам просто 2 презентации. Не считаете? Смотрите, сейчас. Ну, давайте я сейчас сделаю, и вы попробуйте. Да, я вот теперь раздвину. Но это будет почти незаметно. Сейчас вот первая часть конвертируется, и она должна... Ой, я не знаю, она внутри самого вот этого сайта написано просто обрабатывает страницы. К сожалению, не могу вам ответить на этот вопрос. Мне бы в Zoom было так же удобно. Так, это первая презентация, сразу я вторую выгружу. Вы сейчас наблюдаете свою, правильно же, презентацию? Я сейчас обратил внимание, видите текст снизу? Он куда-то уехал. Это... Смотрите, мне кажется, все остальное уже нормально, только главный первый слайд только критичный. Как скажите? Мы тогда сейчас начнем. Ну вот я сейчас наблюдаю, вроде все нормально, все остальные слайды в плане. Вполне возможно. Мы сейчас начнем с Сергеем, тогда вы как сократите, потом мы вам выдадим в конце права самое. Так, ой, секунду, сейчас вам переведу вашу презентацию. Сделать ведущим. Да, сейчас верните первый слайд. Сейчас я, когда дам знак, или вам ведущий даст знак, вы будете на экране, все поймете.
Hi everyone, let's start our next session, and our original chair unfortunately can't attend this part of the conference, so I will be a chair. My name is Maria Burdanova and I'm from Moscow Institute of Physics and Technology, and I actually will give a talk in a few days, so you're very welcome. And we have some technical problems, but our online participants, they are connecting. So our first speaker will be from Moscow State University, and the talk will be about coherent radiation generation by atomic systems in intense arbitrary polarized laser fields. Are you here? Yeah, super. You can start. Thank you.
Okay, thank you.
description has both advantages and disadvantages for description of nonlinear phenomena, nonlinear radiation generation in gas interacted with intent laser fields. And but at the same time, recent results demonstrate the common features in these two nonlinear phenomena. You see that high harmonics and terahertz radiation generation is generated by the same time and in the same experiments, and that means that it may be these two phenomena may have the unique origin, not as it previously supposed that, for example, high harmonics are due to a single atom response and terahertz radiation are due to extended gas response, and which has nonlinearity and so on and so forth. And the main goal of the current study and the main goal of our past recent experiments and recent numerical calculation is to develop a unified theory of coherent radiation generation of both long and short wavelengths radiation by atomic system interacted with arbitrarily polarized laser fields. So this is actually also the challenge for the challenge to the theory, because when we deal with intense laser fields, it is a question which sorts of small parameters can we use. Traditionally, there are two very good small parameters. The laser field strength compared to laser field strength of near atomic atomic field strength, and vice versa. That is why there are a lot of theory which works in a perturbative approach and relativistic approach. And at the same time, the main laser sources can achieve intensity or laser field strength where these two values are comparable, and the ratio of laser field strength compared to intraatomic one is more or less equals to 1. At this non-perturbative approach, this is a challenge to build exact theory. We recently suppose the theory which is named by long wavelength approximation, non-perturbative approach. We start from Schrödinger equation, which has the form of as it demonstrated on the side, and we use two base of edge functions. One is the base of the is the exact solution of boundary value problem for free atom. Another one is the exact solution of the boundary value problem of an atom in external field. These two bases form two orthonormal bases, and we can use it because we can express one wave function in terms of base of agent function of another boundary value problem, and vice versa. These two by using these two sets orthonormal wave functions, basis of the wave functions from the Schrödinger equation, we can goes to the set of differential equation for population amplitudes of discrete and continuum states. This set of equation consists of infinite number of equations, but in the frame of our theory, we build a strong way how to limit the number in order to solve it numerically. But in order when we solve in order to calculate the photo emission spectrum, the short wavelength parts of it can be associated with high harmonics, and long wavelength part of it can be associated with terahertz. It is not enough to solve this set of equations. Once we also need to calculate the spectrum of atomic current density, because in the phi-field zone, the spectrum of atomic current density correspond to the vector potential of the generated radiation. In the frame of the theory, we can calculate atomic current and its spectrum numerically if we know the solution of the set of equation for probability amplitudes and matrix elements of operator V, which can be calculated analytically, and we can use it for collecting the atomic current. This theoretical approach has some benefits in compared to other approaches. One of them is because of the operator V, and not only because of the operator V, but because of this exponential view of this operator. If we express this exponent in terms of electric power, we can understand that this operator V contains nonlinearity of arbitrary values. Also, we can demonstrate that this operator V includes transition between virtual states of arbitrary degree with respect to electric fields. That means that and photonics absorption and emission of photon having energy NH omega are taken into account for arbitrary ways for n. So if this is, let's say, system, if the matter is spherically symmetric and there are no even nonlinearities, operator V knows it automatically, and this is included in operator V automatically, and there are no, for example, even harmonics is generated here, only odd, for example. So this is this exponential, the beautifully of this operator V, this exponential view. So we can use it and take into account on possible nonlinearity, which is in the investigated matter. As for laser field, we can take it in numerical calculation as it in the experiment, for example. So we can use single color, two color, have different polarization and so on, even three color and multicolor polarized. So there are a lot of control parameters of laser fields can be investigated during our proposed method. So the numerical scheme looks like this. So we take laser fields as it in experiment if we wanted to deal with experimental results. So it could be multicolor, arbitrarily polarized, and so on and so forth. We choose the model of an atom. So we choose which levels of atoms we can take into account, or we can throw out because of the transition, because of the smallness of transition and small impact of this transition in the system. And then we calculate the atomic current, which is generally have 3D distribution. And by using Fourier transform, we can look at the spectrum and see that it consists odd and even harmonics. If we calculate the results of the action of two colors field on the single atom. And if we deal with femtosecond laser pulses, we have non-zero signal at zero frequency, which is associated with terahertz radiation. If I repeat, if we deal with a laser pulse of line in a femtosecond time scale, this is how we calculate the response to single atom. But when we wanted to calculate the response of the matter, we can also use some models. We recently present the interference model of extended gas, where we suppose the gas is a set of interacted to each other number of ensemble of items are placed in the media where the laser fields passing through. So each atom interacts with the laser fields, having the parameter dependent on the position of the atom. For example, if we deal with a pulse shape, if we deal with a focusing pulse, so we see that the intensity and spatial characteristic of the pulse changing during the propagation. And we can calculate the response of atom arrayed in different positions inside the gas by a non-perturbative approach, which we discussed recently. And by using this formula, we can calculate the response, the value of the field strength of the generated radiation at the detector, which is, let's say, can be in a far-field zone at the detector. And for terahertz radiation, it is important to have also, let's say, 2D values of gas jets, because we know that the terahertz response has a conical structure. As for the high harmonics, we can limit the interference model to the chain of items, because angular spectrum of harmonics shows us that most of all harmonics are generated to the direction of laser fields propagation. And also, by using this formula, we can calculate the response for given harmonics at the detector. We can calculate the field strength for given harmonics and the variation of some parameters, let's say laser fields or pressure like this, and we see that it could be Gaussianly distributed, or it has additional lobes, and etc. These two component of the theory was verified by the number of experimental results. So we have a successive collaboration with a group of Professor Shkurinov, of group of Professor Gordienko, group of Dr. Potemkin, group of Professor Ganeev, and group of Dr. Guillaume Lambert. And we see that in different types of spectra and terahertz radiation, and in low order harmonics and high order harmonics. This our theory, interference model plus non-perturbative theory gives give results which are nicely coincide with the experimental measured one. So during this talk, I would like to show some recent results on the quasi-phase matching quasi-phase matching contribution. Quasi-phase matching things appearing when we interact multicolored laser fields with a gas with a matter consists of a number of gas jets which are divided one to each other by vacuum spaces. If we see this, if we modulate the response of high harmonics of this nonlinear media interacted with two-color laser field formed by the first and the second harmonics of, let's say, tensor phi laser, we see that in the photoemission spectra there are number of enhanced harmonics, quasi-phase matching enhanced harmonics appearing, and the position of harmonics depending on the sizes of the gas jets. And we see that there are some groups of harmonics which are enhanced. At the same time, in the experiments, on the first peaks was observed, and not the on second and not the third, and so on and so forth. And our model can answer the question why on the first peak can be experimentally observed, but not the second and the third. This is due to strong influence of inaccuracy in depending of the sizes of gas jet. We see that even 1% of inaccuracy gives suppress dramatically the efficiency of the second and the third peak in this spectrum. We also calculate the influence. We also investigate the influence of some parameters of the laser fields and the matter, and we see that some of them influence critically both on the position of the enhanced harmonics and the value of harmonics enhancement. Let's say pressure is one of the most important parameters. The other important parameters is the laser parameter is a wavelength. So if we goes from the near infrared to mid infrared and far infrared, we see that this increase of the laser wavelengths will positively increase the efficiency of the generated radiation. But the position of the enhanced harmonics are not changed in terms of photon energy. As for the terahertz radiation, we also investigated some interesting aspect. For example, we have shown that the angle between the direction of the polarization of the component of two-color laser field are the critical parameter not only for intensity of the generated radiation but also the elasticity. And we demonstrate that there are angles between the polarization direction of two-color laser field where the generated by single atom ellipticity are close to circle, close to 1. In order to calculate the response of a standard gas, we So we also calculate the response of extended gas, not only single atom but extended gas, and during this.
Sergey, I'm very sorry for disturbing you, but you should finish your presentation in a couple of minutes.
I'm also done. Yeah, and we also show that degree of ellipticity and degree of polarization is high enough to prove that generated by extended gas radiation are not randomly polarized but elliptically polarized. And this is also last informative slide of my talk. So we calculate the angular frequency spectrum of the generated radiation by Teragertz by extended gas, and the matter consists of the number of gas jets. And we see that quasi-phase matching are also the critical phenomena for Teragertz radiation generation, and it could increase the efficiency and fix the angular frequency spectrum of the generated radiation. So this is my summary. This more or less repeat which I'm talking. With this, I thank you for your attention, and will be glad to answer to your questions.
Yes, thank you. Thank you for a wonderful talk. Does anyone have any questions? Maybe one short question. We significantly run out of the time. No questions. So let's thank our presenter again. And let's move to another talk. Yes, thank you. And let's move quickly to another talk. This talk will be about optical pump Teragertz probe diagnostics of the ultra-fast carrier dynamics in photoconductive materials, and it will be presented by Vladislava Bulgakova from Prokhorov General Institute of Russian Academy of Science. Please start your talk.
Hello. Hello, dear colleagues. My name is Bulgakova Vladislava, and today I would like to present our setup, optical pump Teragertz probe, and my talk will be about optical pump Teragertz probe diagnostic for the ultrafast carrier dynamics in photoconductive materials. In General Physics Institute, we create a multi-user setup which allows us to measure the optical characteristic of the materials, such as permittivity, refractive index, absorption coefficient, conductivity as a function of a frequency. And also we can measure the carrier dynamics which produced with the light pumping. And also we can measure the photoconductivity as a function of frequency. There is a scheme of experiments. First of all, we can measure the electric field of a Teragertz pulse, which pass through the sample as a function of time. After that, we can stop time of a Teragertz pulses and scan with the optical pumping. We create charge carriers in the sample. It looks like a plasma, and Teragertz radiation scattering and absorption on this plasma. And we can measure the dynamics, its dependence of the electrical field versus pump probe delay time. And we can extract the lifetime of charge carriers. After that, we can stop the optical pump position and measure the dynamic, the distribution of the Teragertz electric field versus time. And using those data, we can calculate the conductivity or photoconductivity of the investigation sample. There is an experimental setup. We use a titan sapphire laser system with a center wavelength of 800 nanometers and 40 femtosecond pulse duration. This radiation divided onto three parts. First of them pass through the today's delay and goes to the detection of a terahertz pulse distribution with the electro-optics. Second of them pass through the optical parametric amplifier and generate optical pulses with a wide range. And the next one pass through the optical parametric amplifier without any and goes to the Teragertz detector. We use the standard Teragertz scheme for generation Teragertz. It's like optical rectification in the nearby lithium crystal. After that, we use a few parabolic mirror to focus the Teragertz radiation onto the sample, and we can carry out our experiments. Next, I will show you the results of the experiments to demonstrate capabilities of our setup. There is an experiment of today's measurements for optical properties of zinc selenium. We can measure the distribution of electric field versus time for free space, for Teragertz radiation in free space and pass through the zinc selenium. And after that, we use a fast Fourier transform to obtain the spectrum of this radiation. And we can calculate using this formula permittivity of the sample or refractive index and absorption coefficient. And these data are in a good agreement with the data which obtained of another collectives for the zinc selenium, for example. Also, we measured the lifetimes of photo-induced charge carriers for different samples to show capability. For example, for a fundamental harmonic, a second harmonic, and after the parametric parametric. This parameter is very important, for example, in a task, the production of photoconductive antenna, because the semiconductors with a short carrier lifetimes can produce the widest electromagnetic pulse after that. Also, we can plot the dependence of the electromagnetic electric field versus optical fluence and extract the data about optical saturation fluence. This parameter is important too, for example, large aperture photoconductive antenna, because it shows us which energy we can extract at a half of maxima without the saturation. Also, we carried out the characterization of plasma-treated carbon nanotubes with the team of Maria Burdanova. And I would like to show you that we can, in our institute, can obtain the absorbance spectrum in a wide range using 3 spectrometers. And this spectrum can show us some transmission peaks of phonons or some conductivity, some regions of conductivity. Also, we measured the lifetime of these samples, and we saw that for one samples with change in pump power, lifetimes not changed, but with the time of plasma treatments, the time of the lifetime of photo-induced charge carriers became smaller. That's why we insert a lot of impurities in the sample with the plasma treatment. Also, I would like to show you the graphs which we could obtain with our setup. We can plot the conductivity as a function of frequency. This is very important for some production task, like using these semiconductors like photodetectors, and we can see how resistive or reactive part of a photoconductivity or conductivity behave. And in conclusion, I would like to remind you that we create a multi-user setup for measuring the optic parameters and some characteristics which very important for creating devices based of the semiconductors. And we will be glad to collaborate with you. Thank you for your attention.
Do you have any questions? So thank you for your talk. Oh, yeah. Sure.
Thank you for your talk. What is the time resolution of your Palm Pro setup?
Time resolution, you mean the dynamics? Now 1 nanosecond, but it depends on the delay movement.
You show the time about several picoseconds. Resolution.
Minimal time resolution can be depend on our pulse of laser pulse. It's a 40 picosecond. That's why 40 picosecond, because femtosecond. Sorry. Yeah.
I think this setup can be applied for biological measurements.
Yeah, I would like yes, but if we should control температурные изменения образца, если они не критичны в пределах мощности, то, скорее всего, да.
Any questions? Let's thank our speaker again. And the last talk, it will be about Teragertz generation from femtosecond plasma channels in both dual color and DC biased and transition regimes. Olga, are you ready? We will have a virtual talk, the last one. Are you ready? We can't hear you. We still can't hear you. Maybe your microphone is switched off. Olga, can you hear us? Кто-нибудь ей может позвонить?
Да-да, здравствуйте, я слышу вас. Yes, I sure can hear you, but I don't see my presentation, although I have just uploaded it.
We will check.
I've uploaded the presentation.
Yeah, we can see your presentation. We can see your presentation, but not the first slide.
I don't see you in my presentation. I would be glad to see you, but I do not. I don't know how to change the slides. How can we proceed? Okay, the moderator is saying that I should switch on the demonstration. And I'm switching on the demonstration of the whole screen. Can see my presentation now. I see it now on the screen and I demonstrate the screen. What
Yes,
about you?
We can see it, but not in full screen.
Okay.
Super,
what about
thank
that?
you.
What
Perfect.
Okay. I do apologize. First of all, that would be my great pleasure to be with you, and I thank the organizers for the very nice conference organized. But I got the call from my overseas trip to my collaborators, so I had to stay at home and to share with you at least through these tools our recent 2-year work with the experimentalists and our group who is doing simulations of detailed study of all Teragertz generation from a single color and DC-biased filamentation. So this is all about gas-based plasma channel, which irradiates waves of different frequencies, and a new insight to it is in the fact that now the best omega to omega generation from Teragertz from filament is already half-closed subject, because the optimization of 0.35 from TICEP 800 pump is already on chip. So this is not like a telecom chip, but a little bit larger, but you already can do spectroscopy with that, and many optimizations has been done, and it's scientifically almost closed subject. It's already in applications. However, what is not done yet is long-range application of this tool with the long distance and terawatt peak power lasers. And at the very beginning of this Teragertz era in 2010 years, there were very nice works that indeed terawatt power lasers outside can also generate Teragertz. And of course, it's very interesting even in the lower part of Teragertz range, and those spectroscopy applications can be done very successfully with lower Teragertz frequencies as well. Look at the spectra of those organic dangerous stuff, right? Beneath 10 Teragertz. Now, the step between omega to omega task and long-range single filament from the terawatt peak power lasers is DC bias. So you can enhance your Teragertz generation using DC biased filaments and try to obtain reasonably good conversion efficiency usable for applications. And what you should know that many years ago in 2000, there was directional diagram studied from those biased filaments as well. And what is interesting, you may see, if you see my arrow, that if you have DC bias applied, you have an order of magnitude larger than a single color filament, and it's already some promising thing. So when you do this single color filament, the straightforward mechanism is light pressure dipole, and you may see that it will be radiating in transverse directions. And that means you will have to have like conical diagram, which Irina Nikolaeva was talking just an hour ago. However, all the interference models, which also the standard routine to apply them, will give you those conical emission. And the order of magnitude is, of course, very low. You see 10 to minus 10 in energy, relatively to the initial pulse duration. Nevertheless, if we have, again, terawatt power laser, it may be essentially improved. Now the pointer motive force can give you again those quadrupole radiation and also conical directional diagram, and you can calculate dipole, quadrupole, and in details construct those directional diagrams. However, enhancement and DC bias is forwardly directed dipole radiation, which will promise you on-axis Teragertz beam distribution, and you already have promising time to -6 conversion efficiency from the initial incoming optical pulse, near infrared, I would say. Okay, so again, the developed models of adding up according to interference modes along the plasma channel well developed and will give you this on-axis emission. So our objective right here is to scale the possible on-table single filament yield to terawatt setups. So this is our challenging task. And first of all, we have to deal better with directional diagrams. And here are the needs for measurements of two-dimensional images. And you can see that starting from 2010, that was a lot of, and even 2007, that was a lot of work, including Professor Shkurinov group and other co-workers, to indeed, for applications, see important on-axis or conical distribution, because it should be directed to the sample. What is the contribution joint of us and our colleagues from Lebedev Physical Institute is studying it with rotating the bolometer. So you have short filament, like shown here, about 1 centimeter. You have a workhorse of titanium sapphire laser with a single filament regime, so the energy is not very large. And the bolometer is rotated horizontally. And also the spherical mirror, which you see now, can be rotated in such a way that it imitates actually rotation of bolometer in the vertical direction. So you have full two-directional diagrams. And Arina was showing that magnificent half conical, half modulated, depending on polarization and frequency resolved data, which I explained theoretically, right? But the problem is that still the conversion efficiency is very low. Here you have the pump like not more than 6 millijoule of input energy, and you may calculate 10 to minus 10. That would not be a lot. Now, if we move up a little bit this initial energy, and for that in Lebedev is 930 nanometer laser, which can be a little bit more powerful. We see that we have multiple filamentation. This is optical beam, single compared to multiple filaments. And this is one of the main results. If you have multiple filaments, all that conical and tricky, conical distribution and modulation with on-axis hole is smoothed out, and you see nice on-axis perfect terahertz distribution, and it may be filtered at different terahertz frequencies, 0.3 terahertz, for example, here. And if we go different filters, you also have on-axis distribution, which is getting narrow, because the larger terahertz frequency, the narrower is the beam you have, which is also important. And as you go further to 1 terahertz, you already have a nice, narrow, well-directed beam from actually stochastic multiple filaments. So this is a very good and promising results. And regarding simulations, we can do it in a single filament regime, as Ira was saying, and we are moving on to multiple filament regime, consistently calculated with terahertz generation. This is first part. Then you can also scale DC biased yield with energy, and it was also done, known for some years now, but it was in a single nicely controlled regime. What was done by Professor Savelev group together with us at Lomonosov Moscow State University Nonlinear Optics building, right? It was made up from a long distance comparatively. So it's not like 1 centimeter, it's like at least half a meter. And it is biased with either one long electrode or multiple short electrodes. And the idea of this experiment is to find out if we can scale up just by adding the electrodes, our terahertz yield from just a single filament without admixture of any other colors, right? The energy is again several tens of millejoules, and the limitations is only in the transmitting optics, not to disturb it. And we know the frequency as well as 0.1, around the maximum is around 0.1 terahertz, and you see the waveform, terahertz waveform as well, you see nice with these multiple filaments, you have nice on-axis terahertz emission. We go further, and you may see that by adding up each next section of the electrodes, you will scale up accordingly the terahertz energy yield, which is very important. That means we can scale it up. We can do it very tricky and complicated in terms of simulational power, but we can match it with the experiment, because we simultaneously propagate optics with the resolution of the field period, and terahertz generation is processed and simulated self-consistently, which is important. And what we see, although not on several meters, but at least on around 20 centimeters propagation path. So if you have one electrode, you have some yield, and it's shown here below by that green point. Then if you scale up to several electrodes, and by adding one by one the yield from each particular electrode, you will see finally some very promising, well, not 2 orders magnitude, but more than 1 order of magnitude increase in terahertz yield with this long electrode technique. And probably this is all which, as a last talk, I won't keep you long. You may ask questions to me. So we have elaborated in details with 2 laboratory angular measurements, actually, and showed that with DC bias, we can go with an on-axis maximum important for applications, and with a DC bias, we can scale it with multiple electrodes. And our next step is just terawatt peak power laser and on-axis terahertz yield from stochastic multiple filaments. Thank you very much. And we thank, of course, Russian Science Foundation.
Thank you for your talk. Do you have any questions? I probably have one. I'm not a specialist in this field of science, terahertz science. So my question is actually, I would like to see your presentation. Olga. Yeah. So on one of your first slides, you showed us, as I clearly understood, could you please scroll it up, down, so down. Next. One more. Next. Sorry. Next.
No, it's fine.
Yeah. Next.
Thanks.
There was an image of, as I clearly understood, it was the image of your terahertz beam as a focus position. It looked like a ring. Yeah, this one. Yeah. You missed
this?
It. The previous one. Yeah, thank you, perfect.
Oh.
So at the middle, is it the image of your terahertz beam as a focus position?
It's actually what is shown here. It's kind of introduction. It's from Shkurinoff laboratory, and it's, you see the date. It's 2012. It was done with terahertz camera, and it was in very, well, relatively powerful omega to omega yield, quite a large percentage. As you might have seen, the percentage is around slightly 0.5% from optic radiation now it's achieved. Well, it may be like 10 to minus 4 energy. It's a lot of Teragertz actually, as compared with what we've been trying to push up these days. You understand? So it's first in olden days. Second, it's omega to omega, and it's traditional ring from omega to omega Teragertz emitter, Teragertz air-based plasmas.
Okay, I understood.
So
Thank
it's
you.
always
Yeah.
it's always conical, and then if you have well, the point is if you say, for example, have DC bias, you may remove those on axis hole and send all of your energy over there in the middle. And another advantage is to put say lower frequencies together with the highest ones in the middle as well, and have more energy.
Thank you. Thank you very much. Any questions?
Thank you for your question.
So let's thank our speaker again.
Thank you very much.
We have one more session. It's a poster session, so it started 40 minutes ago, but we still have it over there, so you will join it.
Thank you.